Good morning, everybody. Just a few words before starting this second day of DTIP 2021. Yesterday we have a good attendance. I'm a bit sad because we have only few questions from the audience, so don't hesitate. After each presentation, we will have a 5-minute time slot. So don't hesitate to raise your hand. You have a button for that. And Yoshio, who will share the first session, will be happy to give you the microphone. And then you can ask your question. And second, after the first two sessions, so after session 3 and 4, we will go to the coffee break, and during the coffee break, all authors will be in a breakout room. So don't hesitate to join them in their breakout room. You can navigate from one breakout room to the other during half an hour, and to have a private or nearly private discussion with the authors. So now is it time to start the session number 3 on MEMS actuators, and it's my pleasure to pass the microphone to Yoshio Mita, who will share this session. Yoshio, your turn.
Yes, good afternoon. Yeah, from Tokyo, by the way. So we are very much excited in Paralympic game currently in Tokyo. So more exciting at DTIP conference. So today, in this session 3, we have 3 exciting papers, and each of paper has 20 minutes. The first paper is entitled the design, analysis, and application of a microelectromagnetic actuator with high force density. The author will be Xiao Xi, China Institute of Electronics Engineering, China Academy of Engineering, Physics, China, U1 and U1. So the first author will be the presenter. The Xiao Xi is currently a researcher in Institute of Electronics Engineering, China Academy of Engineering Physics. His research interests include microsensors and actuators, micromagnetic motors. So he will be making his presentation pre-recorded, I guess. And Pascal is now preparing the videos. So, t'es prêt, Pascal?
Hello, everyone. My name is Zhi Chao from Institute of Electronics Engineering, China Academy of Engineering Physics. Today, I'd like to report about my research. The title is Design, Analysis, and Application of a Microelectromagnetic Actuator with High Force Density.
The sound is not working.
First, I will introduce about the research background.
I'm hearing.
We all know that there are different types of actuators in MEMS field. Among them, the MEMS. Hello.
Si ça marche, hein?
Hello, everyone. My name is Zhi Chao from Institute of Electronics Engineering, China Academy of Engineering Physics. Today, I'd like to report about my research. The title is Design, Analysis, and Application of a Microelectromagnetic Actuator with High Force Density. First, I will introduce about the research background. We all know that there are different types of actuators in MEMS field. Among them, the mainstream are electrostatic, electromagnetic, and piezoelectric. Compared with other driving principles, electromagnetic actuator has the advantages of low actuation voltage, long working distance, and non-contact actuation. However, for conventional planar-type electromagnetic actuators, usually it consists of the planar-type film magnet like this and the spiral-shaped microcoil like this. It usually generates very small force. To cope with these shortcomings, previously in our group, we proposed a chessboard-type electromagnetic actuator. As indicated in this figure, it consists of the chessboard pattern permanent magnet as well as the mesh-type microcoils. And in this figure, we can see that compared with the conventional one, the generated force, which is around 400 micronewton, when the gap between the coil and the magnet is around 0 to 200 micrometer, the generated force of this chessboard pattern actuator is rather higher compared with the conventional one, so that it demonstrates the high force capability of this actuator. However, the current input is 0.2 ampere, so it can limit it only to short time usage. And the further increasing force is required for its applications. So the objective of this research is to realize the high force electromagnetic actuator for long time use. And the solution we proposed in this research is to replace this thin film with thick film, and then to optimize the single-turn mesh-type coil into multi-turns. Then comes to the actuator design. This is a designed microelectromagnetic actuator, which consists of the chessboard magnet pattern, also we call it the mover, and the 3D microcoil, we also call it the stator. The stator has the double side and multi-turn configuration. Let's see about the detailed design of the microcoil. If we input current into the microcoil in like the arrow indicate, it first rotates this like this direction. Then from the central metal wire, it gets upper and then rotates like this way. The upper and the bottom rotational direction is the same. Then it moves to the next adjacent unit. We can see that it rotates the different direction with its adjacent ones, so that it can generate the magnetic field pattern like this. Also, a chessboard magnetic field pattern is generated by the microcoil, which coincides well with the mover. This shows the design parameter of the mover. We use neodymium permanent magnet for the material, and the type is N44UH. The dimension is 0.8 millimeter square and then 0.3 millimeter thick. The interval is filled with epoxy, and the back yoke is used the SAS 430, which is good for magnetic field induction. For the stator, we use the silicon as a substrate, and then we input the copper in the slot of the silicon. And the turn number for each unit is 8 turns, and the cross section of the coil is designed to be 0.05 millimeter and the depth 0.05 millimeter. This shows the force simulation between the magnet and the coil. We can see that the input current is 0.1 ampere. When the gap changes from 20 micrometer to 300 micrometer, the force gradually decreases from 10 millinewton to around 2.5 millinewton. When the current direction changes, the generated force direction also changes, finally getting the repulsive and attractive force. Then comes to the actuator fabrication. This shows the fabrication process. For the mover, we first sink the magnet to 300 micrometer, then bonding with steel. After photolithography and etching, we get the chessboard pattern. Then we filled with epoxy and polishing. Finally, we use magnetization. For the stator, on the silicon substrate, we do oxidation, photolithography, wet and dry etching. Finally, we do oxidation and copper electroplating and polishing. This is the fabricated chessboard pattern of the mover, and the unit measured is 0.81 millimeter, which is close to the design value 0.8 millimeter. And this shows the microcoil fabricated result, and this shows the enlarged view and the X-ray scanned view. Then comes to the evaluation. First, for the microcoil, in order to test its connectivity, we measured the resistance and calculated the resistance. For the calculation, we use this equation. And the measured value is 8.8 ohm, and the measured value is 13 ohm. The difference between the calculated value and the measured value is maybe caused by the over-polish during the microcoil fabrication. In order to evaluate the microcoil performance, we input the DC current into the microcoil for a long time. And we change the current amplitude from 0.1 ampere to 0.4 ampere. And this figure shows the result of the calculated temperature and measured temperature. To calculate the temperature, we use this equation, in which R1 is the resistance at room temperature T1, and R2 is the resistance as the calculated temperature T2. And alpha is the temperature coefficient. In this figure, the dashed line is the calculated one, and the solid line is the measured one. We can see that for all the cases, the temperature finally reaches to a stable value, indicating that it reaches to a thermal equilibrium state. And even if we input current of 0.4 ampere, the measured temperature reaches around 70 degrees, indicating that for the long time use, the current is not broken. Then, to measure the force generated between the mover and the stator, we use electronic force balance. And then this shows the measurement configuration. The mover is attached to a precision stage, and the gap is adjusted between by the precision stage. By input different current into the stator, the force will be generated, and the force can be measured by the electronic balance. The measurement result shows is in this way. Even if we input 0.4 ampere current, the force is around 70 millinewton, and the force direction can be seen by this figure. We will change the direction of the current, the force direction also changes. However, the measured force is smaller than the simulated one. The amplitude is around 40%. This may be caused by the misalignment effect, which is demonstrated here. It means that there is not aligned between, there is the stator and the mover is not aligned in different direction. The force will degrade. We analyze the misalignment in different situations. Situation 1 is the misalignment in X translational freedom, and situation 2 is the misalignment in the X rotational. And situation 3 is the misalignment in Z directional axis. And then we simulate the performance of the magnetic force. We can see that for the ideal simulation, the situation 3 has degraded little, and situation 1 means the translational direction has decreased the performance to around 10%. And for the situation 2, the X directional rotational misalignment degrades the performance to around 20%. And in real actuation situation, it is a combination of different misalignment, so that it caused the degradation of the generated electromagnetic force. Then this table compares the performance of this work compared with the previous work. In this work, we define the force density parameters, which is defined by the force divided by size, by volume per unit ampere input. And then the force density of this work is 0.96 millinewton per ampere per millimeter square, which is 3 times in our previous result. Furthermore, this actuator can input stable current of 0.4 ampere for long-time use, which is also a good advancement. In order to test the application of this actuator, we apply this mover with the planar spring like this, and then assembled a micro actuator. The planar spring stiffness is 269 Newton per meter, calculated by the finite element method. This shows the picture. And then to measure the displacement, we use a displacement sensor. This is the result. First, we input different current into the actuator, and then we measure the displacement. We find that it fits well with the linear relationship. By using this, we calculate the force by using the stiffness in previous slide. And then the calculated force together with the measured force are compared in this figure. We find them, they coincide well, indicating the usability of this actuator. Then comes to the conclusion and the future work. In this research, a planar-type microelectromagnetic actuator with high force density is designed, fabricated, and evaluated. The microcoil can withstand 0.4 ampere input, that is 160 ampere per millimeter squares, and the misalignment degrades the performance to around 40%. Even if misalignment exists, the force density of the actuator reaches 0.69 millinewton per ampere per millimeter squares. Furthermore, this actuator drives a spring. The calculated and measured force coincide well. For the future work, first, we will further increase the force density of this actuator by integrating the ferromagnetic cores. And then we will apply this actuator into micro switch. That's all for my research. Thank you for your listening.
So thank you very much for this nice talk. So I think the author is here. So joining with us.
Yes, I'm here.
So good afternoon. So nice work. So now the paper is open for questions and comments from the audience. Yes. So the first one, 1, 2, 3. So first person, Abdel Kim Talvi, please.
Okay, thank you, Chair. Thank you for this nice presentation. I have a question, because during the video we don't see the slide, because I don't understand how the performance is increased when you move from single coils to multi-coils. Not only multi-coils, but I see that you need also to do some microstructuration of the magnetic materials. Can you just explain how you improve the performance, because we lost the slide during the presentation?
You want to know why the force density can be increased from the...
Yes. What is the main reason?
Okay. Can you see my desktop?
Try. Try to make a share.
Let me see.
Can you share your... Probably, yes.
Okay. Maybe this one. Can you see it?
Yeah, it's coming. It is coming. It is
coming. Just maybe during the
that's coming.
Okay.
That's coming.
Okay.
Yes.
Okay. Yes. For the previous
actuator in which we use this chessboard type magnet, and then in this research we use thick film rather than the thin film. When we design the motors, we know there is an index called PC value, which means the ratio between the length and its thickness. In the previous research, the length is around 0.5 millimeter and the thickness is around 6 micrometer. So it means it's still a very flat type. In the new one, for the thick film, the magnet thickness is 0.3 millimeter and the implant size is 0.8. So that means it is more like a very bulk magnet. I mean, the thickness is near its length and width, so that the surface magnetic field is larger than previous one.
But the question is, why do you use such structured magnetic materials instead of homogeneous materials? Because if I say you divide single coil on several small coil,
yeah,
and also you divide the homogeneous magnet on small magnet, there is any idea why we don't just use simple magnet?
You mean why I do not use only one flat magnet?
Yeah.
But I divided them into the chessboard pattern.
And big coil.
Okay.
Yes.
Because I understand big coil is to come to the solenoid form. This is okay, but for magnet, why you divide the magnet to small?
Yeah.
What is the advantage of that?
Yes, in this, can you see this one?
Yes. Yeah.
If we use only the one piece of magnet without segmentation, the generated force is small. Because the surface magnetization for this one is only limited to the edge part. If we measure the surface magnetization, the surface magnetic flux density is only in the edge. So the edge can generate more magnetic flux for this thin film magnet. If we want to increase force, we must divide the magnet into small pieces.
It means that you want to put the magnet behind the center of mini coil. It means that you have the flux, it's directly perpendicular, and you get more attraction between magnet and coil. Is that?
Yeah, yes. Not only in the edge, but also center.
Okay.
Okay. Very interesting. So there are still two persons raising hand, but I think it is just 20 minutes. So unless there is a very short question, Paco, Ambia, I would like to call. Oh yes, do you have very short question?
It's just about the fabrication of, but maybe I can ask in the break out.
Probably. Yeah. Breakout room. Yes, fruitful discussion. Yeah. So let's thank the author again with for some kind of reaction. Let's react for him. So thank you very much.
Okay.
Thank you. Yeah. So and then the further discussion can be done at the breakout room after the session has finished. So let's go to the second presentation. That will be efficient flow generation of bionically inspired. I like bio-inspired stuff as well. Microactuator by dedicated optimized electrical excitation. So the author are the 1, 2, 3, 4, 5, 4 person. Technical University of Munich and Germany. So the author, the presenter will be, I think, Robert. I saw you. Hello.
Yeah, I'm here. Hello.
Yes. Good morning. So he's a research associate at the Technical University of Hamburg. Prior to his employment, he did research as a student at Technical University of Munich for the chair of physics of electrotechnology. So congratulations for your new post, and go ahead. Yes.
Can you see the slides?
Yes, go ahead.
Perfectly. So today I will present some of the research that I've done as part of my master thesis at the Technical University Munich in Germany, as noted before. And the title here is a bit different because we changed it some weeks ago, but I think it's not updated. So it's about the optimization of the electrical excitation for a bionically inspired fluid actuator. And here on the first slide, we can see the actuator, a schematic representation. And the front part here is flexible. So with our electrical signal, we will actuate the front part up and down, and the rest of the device is fixed. And here we can see a measurement animation. So I measured the behavior and animated it. And here we can see how the flexible part moves up and down. And the interesting behavior here is that we can see a wave propagating along the device. And this way we can push fluid forward. In our analysis, we mostly used air as fluid. However, we could use, for example, water or any gas too. And this principle of a wave propagating along the device is called undulation. And for undulation, the specific case is that we have a phase difference or phase shift between the middle point and the leading edge point of 90 degrees. I will go more into these topics later on. And the principle of undulation is adopted from fish. So fish can move their tail fin in such manner, and this allows them to move really efficient. And this way they create these bilateral vortices, and this results in a jet stream and results in the high efficiency of the undulation motion pattern. And today, first we will have a short look on the structural composition. After that, we will have, or I will present the dynamic behavior of the device. And the last part of my presentation will really be about the electrical excitation and how we developed this principle I presented in the paper. For the device, we use a silicon insulator or Zoe substrate. And this substrate consists of 2 silicon layers and has a silicon oxide layer in between. And onto this substrate, we apply 3 material layers, molybdenum and aluminum nitride. So we have 2 electrodes, which are above and below the aluminum nitride layer. And this enables us to use the piezoelectric effect to create this excitation of the device. And when we apply a harmonic electrical signal, we can create a harmonic electrical excitation. And the aluminum layer is divided into 2 electrodes, here shown as front electrode and rear electrode. And they can be contacted separately with such pads here. And the molybdenum electrode is used as ground or reference electrode, and it's not divided like the aluminum electrode. For the dimensions, we have a length of the leading edge of 868.6 micrometers. So the general dimensions are below 1 micrometer, 1 millimeter, sorry. And the length of the flexible part here is 300 micrometers. However, when we look at the dynamic behavior on the next slides, we have to consider some manufacturing tolerances. And during the manufacturing process, for example, under etching, which is a common issue, could occur and increase this length of the flexible part, and which has therefore a strong influence onto the dynamic behavior. And this has to be considered when we want to determine an electrical signal for the excitation. since the operating point, I will show later, is really sensitive, and we have to account for such deviations from the ideal model we want to manufacture, or ideal device. And here we can see some measurements I've done with a laser Doppler vibrometer. And here we can see the first 3 resonance frequencies of the device. The first one is slightly below 30 kilohertz, and we can see the leading edge here in front is moving just up and down, and the points move all in phase. For the second resonance frequency, we can see a strong twisting of the device here, left to right. And for the third resonance frequency, the device is bending really strongly. And for our analysis, really, it was important to have no such bending like for the second or third resonance frequency. Therefore, we only considered frequencies below this first resonance frequency, here denoted as 28.3 kilohertz here. Which is because the device behaves nonlinear exactly around this resonance frequency. Therefore, we left a gap of 500 hertz to the resonance frequency itself. And we will consider in the following presentation only the frequencies between 1 kilohertz and these 28.3 kilohertz. And here we can see exactly this dynamic behavior. This is the one thing I want to show on this slide, and the maybe more important thing is the notation down here. Because in the following, I will refer to the, I will divide the electrode contribution into the contribution from the rear electrode and from the front electrode, which will be denoted with an F for the front electrode and the H for the rear electrode. And as I noted at the beginning of the presentation, 2 points, and the phase shift is important for annihilation. So we will look at the middle point between the electrodes and the leading edge point. And we will optimize the phase shift in the dynamic motion between those 2 points. So when we excite, for example, the rear electrode, we can look at the amplitude of the middle point here denoted with an M, and this is shown here. So we have in blue the amplitude when we excite the rear electrode, and here we can see the dynamic frequency response when we actuate the device with a harmonic signal. In this case, a sine wave was used, and the resonance frequency here can be seen too. When we look at the excitation of the front electrode, here denoted in green, then we can see the amplitude is much smaller. And for the following, it's important that the amplitude has the same order of magnitude. Therefore, we used a scaling of the electrical signal, and this results in this orange curve here, where the scaling is applied. So we have 2 excitation signals, which will be used in the following slides here in equation 1. And for the rear electrode, we scaled this voltage amplitude by the factor of 0.33. And in both cases, a sine wave is applied to each electrode. Since the aluminum electrode here is separated, we can apply a phase shift between the electrodes too, which is denoted here as electrical phase, P electrical. And this electrical phase shift we can apply to the front electrode. So here I will present the dynamic frequency response as a vector diagram. So this vector diagram is always valid for one frequency, because we have these amplitudes which are complex vectors. So we have a phase of the amplitude and we have the magnitude itself. This is shown here, is always valid for one frequency, and we can determine these vectors here. So we have the actuation of the rear electrode with an H and can measure or simulate the motion of the 2 points, the leading edge point and the middle point. And the other way, we can just contact the front electrode and measure how those 2 points move in respective. So these are 2 measurements or simulations for a certain frequency range, and the sampling rate is important there too. But yeah, from this simulations, we can just draw this vector diagram here. And due to the leverage effect, it somehow makes sense that when we actuate the rear electrode, the motion of the middle point is smaller than the leading edge point. And in addition, we can just contact the front electrode, have a contribution too. And those 2 vectors are again in phase because we only contact 1 electrode. And now we can numerically introduce the electrical phase between those 2 vectors. And the electrical phase leads to a rotation between those 2 vectors here. And based on linearity, or if you assume for now that the device behaves linear, the sum or the dynamic movement of each of those points is the sum of the individual excitations. So the total motion of the leading edge point, here denoted as PF, is the sum of the rear electrode and front electrode, considering the electrical phase applied in this case. And the motion between those 2 points, between the leading edge point and the middle point, has a mechanical phase. And this is the important phase for the undulation or determining an excitation for undulation. So this way we can describe frequency dependent, but we can describe in general how the mechanical phase and the motion of the leading edge point and middle point behaves. And for that, we only need 2 measurements, 2 frequency dependent measurements or simulations to determine these 4 values here. And these can be easily achieved, or this can be easily achieved. And on the last 2 slides, I will go a bit deeper into the relation between the mechanical phase, the electrical phase, and the motion or the amplitude of the leading edge point. Here we can see the result of this vector diagram optimization for 2 different frequencies. And for those 2 frequencies, we look at the mechanical phase. It depends on the electrical phase, and the same for the amplitude of the leading edge point. And what I showed earlier, this principle is here denoted as a solid line. So these 2 solid lines in blue and yellow. And what we can see is that when we have a closer look maybe at the amplitude for 0 degrees electrical phase is maximum, which somehow makes sense when these 2 vectors point in the same direction, is minimal as at 180 degrees, which makes sense too, since the vectors point in opposite directions, and increases then again when we go to 360 or 0 degrees again. For the mechanical phase, we can see we have a maximum here at around 180 degrees. And as I pointed out earlier, we want to optimize for a mechanical phase of 90 degrees, which is somewhere in this region for undulation. We can see to the strong frequency dependency of the amplitude and of the mechanical phase too. So it is not identical for 10 and 20 kilohertz. And to validate our method, we decided to perform some measurements. And for those, these measurements are here denoted as those points. And for these measurements, we really used the respective electrical signal with the electrical phase denoted here. So we really contacted both electrodes and looked at the behavior of this device, and it almost perfectly matched matched the results of our method. And here I want to maybe point out a bit clearer the difference between the undulation case and a simple, what I refer to as oscillation, where we just apply a signal with with a low electrical phase. And this is shown here on the last slide or second last slide. Here we can see in red what happens when we have an electrical phase of 300 degrees. All points almost move in phase down. So this is the time evolution of the bending line. Here, the bending line we can see down here. It is the bending line where those 2 points we optimized for lie on. And we can see all those points move in phase down in the time frame we show here. And for the undulation case, which is at an electrical phase of 183 degrees, we can clearly see the strong bending of the actuator here. And when we look maybe here, here's the zero crossing exactly between those two electrodes at the middle point. And here this point has a maximum. So maybe to point out a bit, this is really almost perfectly the 90 degrees phase shift between those 2 points we achieved here. And this brings me to the conclusion of my presentation. So today I presented a theoretical approach to optimize the electrical excitation for this micromechanical device. And the main advantage is that we can optimize the excitation without parametric simulations, which are often really time consuming. And in addition, we don't even need a simulation model. And if we really want to account for all these manufacturing tolerances we might have or inaccuracies, then it is often really time consuming to calibrate an exact model which can deliver such results for an electrical excitation and can be and those results often can't be validated for the real model because there are some deviations. And this way we do not need anymore some trial and error measurements where we can see, okay, the simulation results weren't really accurate. We need to redefine the model and measure again. So we don't need that anymore. And because we can use, for this method, we can really use simulation data, or we can use the measurement values. Therefore, we can account for manufacturing tolerances. And in the end, it doesn't really matter because we can just measure it and need no simulations. Thank you for your attention.
Oh, thank you very much for the presentations. I wanted to open the questions, but you have just running up your time. 20 minutes.
Yeah, I just saw it was a bit long. Sorry for that.
Well, no. You took your time to explain what has been your contribution actually. Yeah. So unless there is a very, very short questions, I'm sorry to say, but so
I think the hand was up earlier too. So.
Yeah, I think yes, that has been Emilia.
Yes, thank you. I will put my video also. I saw you made the measurements by laser Doppler.
Yeah.
Don't you have how much time does it take for one measurement?
I'm seconds. I'm not sure if below 10 seconds, below 5 seconds. So in the region of seconds.
Okay.
So you need much more time to contact the electrodes compared to the measurement time.
Oh, because your images, your moving images were very impressive, and I was supposing that it would take some time. So I will come in the breakout room later.
Yeah.
So thank you.
So let's thank the speaker with some reaction probably. Go. Yes. So then we will go to the last presentation of my session. The title as Wind Tunnel Integration of micromagnetomechanical system, difficult to pronounce, microballs, for flow control experiments. Thomas Arnoux, and I think that he will be presenting by video. So Pascal will be, it's
Morning,
ready.
everyone. My name is Thomas Arnoux. I'm a second year PhD student from the IMN, the Institute of Electronic, Microelectronic, and Nanotechnology in Lille. My PhD is being carried out in partnership with the ONERA and is part of the ANR Camelot Modval. It is funded by the Region Hauts-de-France and by the DGA and focuses on flow control application with MEMS technologies. In this presentation on the use of microvalves for flow control experiments on a cavity, I will briefly describe the general context of my PhD, then present the characterization of the magnetically actuated microvalves and illustrate their use to control the flow over an open cavity. Given the IPCC data of 2014, 14% of greenhouse gases are emitted by our means of transportation. They are responsible for other polluting emissions, such as NOx, SOx, responsible for noise radiation and can undergo structural vibrations. Challenges are therefore to reduce fuel consumption, decrease the polluting emissions, and curb noise radiations and vibrations generated by flow instabilities. The aim of my PhD is to apply flow control strategies and modify a flow general behavior with a space and time localized perturbation thanks to MEMS technologies. In this work, it has to be proved that a linear array of MEMS actuators can be integrated on a cavity in order to perform open-loop flow control experiments. The flow developing over a cavity is characterized by a complex dynamics, which I will describe later. In this experimental approach, the MEMS actuators used are magnetically actuated microvalves developed at the IMN and integrated on the cavity upstream corner. Sensors to be used are Q-light sensors in order to perform unsteady pressure measurements. These sensors are to be placed on the cavity downstream corner. The flow over an open cavity is nonlinear and complex dynamic phenomena develop in it. Tam and Bloch developed a mathematical model in 1978 to describe the coupling between the shear layer instabilities and the self-sustained oscillations. The flow development can be described as follows. Firstly, the boundary layer separates at the cavity upstream corner and evolves as the shear layer. This shear layer undergoes hydrodynamic instabilities over the cavity and impacts the downstream corner. This induces acoustic waves propagating upstream and exciting the shear layer instabilities. These instabilities are responsible for noise radiation and structural vibrations. That's why it is of interest to dump them. The magnetically actuated microvalves used to control these instabilities are developed at the IMN. These microvalves consist in a pressurized air inlet, a microchannel with two inner walls, and a semi-metric outlet. The microchannel is surmounted by a flexible resonator made in PDMS on which is fixed a silicium pad. On this pad, a couple of permanent magnets is fixed. With this design, two different actuation modes are possible. One with a quasi-steady jet, no force is applied to the silicium pad. The pressure difference between the actuator inlet and outlet induces a flow. Another one consisting in a pulse jet. A pressure difference is applied through the actuator and an electrical signal runs in the coil surrounding the magnets. The induced magnetic field moves the resonator up and down, modulating the channel 8. This results in a modulation of the outlet velocity. A set of 15 microvalves has been mounted and integrated as a linear array on a wall designed to form the cavity upstream corner. It was installed on the test bench to perform hot wire measurements in order to characterize both the quasi-steady jet and the pulse jet exiting the actuators. For these measurements, one microvalve was supplied with a pressure difference of 150 millibar, corresponding to a mass flow of 1.5 liters per minute. Hot wire measurements were performed in the ZY and XY planes. Measurements were performed with a sampling frequency of 20 kHz and a duration of 1 second for each point. Considering the first mapping on the left in the YZ plane, the jet outlet angle of 45 degrees can be observed. This is due to the jet adapter changing the outlet hole to a slot. On this mapping, the jet dispersion can be also observed. For Z equals 3 mm, the jet spreads over 3 mm, and for Z equals 6 mm, the jet spreads over 5 mm. Considering the mapping in the XY plane, performed for Z equals 0.5 mm, it can be observed that the velocity is centered on the slot exit and spreads over the entire slot length of 12 mm. The maximum velocity is about 25 meters per second and decreases as the distance to the slot center is increased. Once the quasi-steady jets were characterized, pulsed jets were studied. For these measurements, the entire array was supplied with a pressure difference of 250 millibar. One microvalve is supplied with an electrical signal of this form on the left. Electrical signals used were sine wave with frequencies varying between 20 Hz and 380 Hz, and with amplitudes of 0.5, 1, 1.5, and 2 volt, yielding electrical powers ranging from 100 milliwatt up to 400 milliwatt. Measurements were performed with a sampling frequency of 20 kHz. Filtered velocity measurements are presented here for a frequency of 20 Hz for the 4 different amplitudes. The velocity is modulated around a mean value of 22 meters per second, and the modulation depth is increased with A. Same results were observed for all the tested frequencies, as presented here in this chart, where the evolution of the outlet velocity can be observed against time for a frequency of 240 Hz. From these measurements, it was observed that the actuators behave linearly over a large frequency band. Therefore, the microvalve transfer function was computed. This transfer function, defined as the ratio between the outwire velocity measurements and the input signal, is presented below. The both diagrams are decomposed into the gain and the phase. Considering both the gain and phase diagrams, the curves are superimposed for all the tested amplitudes, confirming the actuator's linear behavior. An exception may be noticed considering the gain curve for A equals 2 volts and for frequencies above 250 Hz. This might be explained by the fact that alternative oscillation modes of the pad appear for these conditions. The entire set of microvalves was tested, yielding similar results. At this point, a linear array of 15 microvalves has been assembled, and both their quasi-steady and pulsed jets were characterized. The actuators proved to behave linearly on a large frequency band. This linear array has now to be integrated on a cavity upstream corner to perform open-loop flow control experiments. First, the flow dynamics has to be characterized, and then different types of forcing will be implemented. The wind tunnel on which the actuators are to be integrated is the S19 wind tunnel from the Onera model. This wind tunnel consists in a plenum chamber where measurements of the total pressure and temperature are performed in order to determine the velocity. The cavity is placed in the test section where the upcoming boundary layer is turbulent. The actuators are placed on the cavity upstream corner, and sensors are located on the downstream corner where the cavity dynamics is the most amplified. Pictures of the integration are presented here. On the left side, the wind tunnel test section with the cavity is presented. The cavity has a length of 134 millimeters and a depth of 900 millimeters. The flow runs from the left to the right side. On the right side, the integration of the actuators is presented. The actuators are flush mounted on the upstream cavity corner. First measurements in the wind tunnel were dedicated to the flow dynamics characterization. The aim is to find a flow regime characterized by harmonic low-frequency oscillations. 3 free-stream velocities were identified: 20 meters per second, 30 meters per second, and 34 meters per second. The flow spectrum presented here corresponds to a free-stream velocity of 20 meters per second. It has been inferred on the pressure measurements acquired over 45 seconds with a sampling frequency of 10 kHz. The spectrum was computed with a Welsh algorithm based on 60 windows and 50% overlap, yielding a frequency resolution of 0.11 Hz. The sound pressure level based on the spectrum and on this equation is presented here against frequencies. This spectrum is composed of a peak at 50 Hz due to electrical noise. The 3 interesting frequencies are at 128.6 Hz, 257.2 Hz, and 385.9 Hz. The second and third frequencies correspond to harmonics of the first frequency, therefore characterizing a low-frequency oscillating flow regime. First control experiments focused on the effect of quasi-steady jets on the flow. The following figure illustrates this effect considering a free-stream velocity of 20 meters per second. The blue curve corresponds to the cavity natural dynamics without forcing. The red dashed curve corresponds to the cavity spectrum with the effect of quasi-steady jets for a driving pressure of 290 millibar. it can be observed that the fundamental frequency amplitude is reduced by 20 dB and that the first harmonic is totally damped. The effect of the quasi-steady jets depends on the free stream velocity and on the driving pressure. These measurements and spectral comparison were performed for the 3 flow regimes identified and for driving pressures ranging from 0 millibar up to 290 millibar. The following chart highlights the fundamental frequency amplitude reduction obtained with the quasi-steady jets depending on the flow regime considered. It can be observed that more the driving pressure is increased, the more the fundamental frequency sound pressure level is decreased. Also, as the free stream velocity is increased, the actuator's authority on the flow is decreased. Considering the blue curve for a free stream velocity of 20 meters per second, it can be observed that for a driving pressure of 290 millibar, the sound pressure level difference is about 20 dB. To compare the effect of quasi-steady jets in this study case with former studies on cavity flow, the blowing coefficient BC has been calculated. It corresponds to the ratio between the actuator and the wind tunnel mass flows. This chart represents the BC coefficient in percent for different studies as a function of the sound pressure level reduction reached for the fundamental frequency. An efficient control method would have a low blowing coefficient value and a high sound pressure level reduction. It can be observed that the microvalve used in this study enabled to reach a satisfying compromise between performance and energy consumption. Then, the effect of pulse jets on the flow dynamics were observed. The following graph illustrates the cavity flow dynamics with the pulse jets for a frequency of 180 Hz and amplitudes of 1 volt and 2 volts, and for a driving pressure of 250 millibar. The blue curve represents the cavity natural dynamics without forcing, and the red one corresponds to the effect of the quasi-steady jets. The yellow and purple ones correspond to the effect of pulse jets on the cavity dynamics, respectively for amplitudes of 1 volt and 2 volt. For these two last curves, it can be observed that the actuator's pulsating frequency appears in the cavity dynamics. The peak amplitude depends on the input signal amplitude. This effect was observed for all the tested frequencies away from the cavity fundamental frequency. The tested frequencies span from 80 Hz up to 400 Hz. A second effect could be observed at this frequency of 180 Hz, as the fundamental frequency amplitude is further reduced by 3 dB. However, this effect depends on both the actuation frequency and on the forcing amplitude. Therefore, no general consideration could be drawn regarding this effect. Further tests were carried out with pulsating frequencies close to the cavity fundamental frequency of 128.6 Hz. Harmonic forcings were implemented with a driving pressure of 290 millibar, amplitudes of 1 volt and 2 volt, and for frequencies in the range of 126 Hz up to 131 Hz, with a step frequency of 0.2 Hz. The following chart presents the evolution of the cavity resonant frequency against the forcing frequency. The blue curve corresponds to forcings with an amplitude of 2 volt, while the red one corresponds to forcings with an amplitude of 1 volt. Depending on the forcing amplitude, it can be observed that over a given range, the cavity fundamental frequency is shifted towards the actuation frequency. This is a locking phenomenon which capture bandwidth depends on the forcing amplitude. To conclude this presentation, microvalves used in these experiments can generate both quasi-steady jets and pulse jet. The actuators prove to behave linearly over a large frequency band. Furthermore, the jet outlet was adapted to the study case of the cavity. Considering the open-loop test campaign, the flow dynamics was firstly characterized. Then, quasi-steady jets proved to be able to reduce the cavity fundamental frequency amplitude by 20 dB for a free stream velocity of 20 meters per second. Pulse jets dynamics superimposed with the cavity dynamics for frequencies away from the fundamental one. For frequencies close to the fundamental one, a locking phenomenon has been brought to light. In future works, these results will be used to perform a closed-loop control of the cavity flow. Thank you for your attention.
So, I'm looking for, yes, Thomas. Bonjour. So if there is some, we have a couple of minutes actually. So if some of the audience have questions on the microactuator and or the performance or on the experiment. Emil.
Again, hello. I thank you for a very interesting talk. I had just a question because you have lots of you present lots of things, and about the role of your institutions. I suppose your actuator is fabricated at UMN, and that the tunnel and the trials are in Onera, I suppose. Is that the case?
Yes, it is.
And is it easy to manage this? I don't remember, but you had Onera somewhere, so you have to move along and to fabricate something in some place and to try in some place else.
Yes, actually the microwaves are being built at the IEMN.
Mm-hmm.
And then I spent a few months in the Onera Meudon next to Paris.
Okay.
And
so
we have some slots to carry out the experiments.
Okay, because the experiment, this wind tunnel is shared, I suppose, and
yes.
Then you need to. Okay.
It's also used for different experiments. So mine is only one part.
So your experiments are also a big organization experiment.
Yes.
Okay. Thank you.
Yeah. Actually, to control the flow by MEMS is very old, but still new ideas. Because as early as in MEMS 98, Yu Chong-tai professor's group made a balloon actuator to control the wind, turbulence on the wing or something like that. So it reminded me of that very old technologies when I was a student. Yeah.
Yes,
well,
flow control is very.
Yeah,
it's a very old discipline, but the use of MEMS is quite new. About 20 years ago.
Actually, 20 years ago already they said, but they are not that much elaborated. So, but my last short question is that: do you open all the valves synchronously or made differently?
No, all the valves are driven with the same signals. They all behave the same way.
Yep. Well, when you change some kind of dephasing or something like that, that may make another function.
Yes, we could have a three-dimensional flow, which we want to avoid because it's a bit simpler, a bit easier to handle a 2D flow. So that's why we only drive the microwaves with the same signal.
Okay. Very good. So now we have just run up the time. Let's thank Thomas very much with some reactions. Or we can unfortunately Zoom mutes the clapping, so we only can do the by reaction. Yes. So the session actuator is finished, and I think that really the next session will start. So I will pass the microphone to Corinne.
Yes, thank you, Yoshio. So thank you for sharing this session. And now quickly we jump to the next session that will be shared by Corinne.
Thank you, Pascal. Thank you, Yoshio, too. Congratulations for your French also. Good morning or afternoon to the attendees. Yes, I'm Corinne Desjous, professor at Bordeaux INP in southwest of France. My research main topics are on resonant wave-based chemical sensor, and I have great feeling for the environmental impact and things like that. So this special session targets environment-friendly and sustainable approaches for sensor and actuators. And it addresses, in fact, the whole topics of the conference, but with contributions paying a specific attention to this impact on the environment, considering the entire life cycle of the device, of the products, in fact. Okay, so perhaps we can go to the first speaker. Is Vivian Hong there? Okay.
Yes, yes, hello. Yes.
Hello. So you have obtained both Master Science and PhD degrees of electrical engineering from University of Tokyo in 2005 and 2008, respectively. During your PhD, you spent 2 years in a multi-scale robotic group in the Institute of Robotics and Intelligent Systems in Switzerland, in Zurich, ETH. And then for about 2 years, you worked as a postdoc at Sorbonne University, France. And in 2010, you joined the Center for Nanoelectronics as a CNRS research scientist. Since last year, you are visiting to LIMS CNRS in Tokyo, University of Tokyo. And your research interest covers micro nano robotics, micro nanofluidics, lab on a chip, 3D helical nanobelts, in situ scan electron microscopy characterization, nano manipulation, and nano assembly. So I guess you have amazing things to show us and to describe. Can you share your screen?
Okay, thank you. Yes, thank you, Chairperson, and so thank you very much for introducing my presentation. So this is Guilhem Huang from the LIMS laboratory at University of Tokyo, which is CNRS International Joint Laboratory with the University of Tokyo. So today I'm going to give a talk on the miniaturized sub-transformable swimmer for environmentally friendly and sustainable fluidic carrier. Okay, and so first slide illustrate as all of us are very today concerned about this pandemic situation. Biological laboratory is very important doing functionalities to have disease diagnostics, especially. And if you look inside of the ordinary routine and life in the biological laboratory, they have diagnostic devices and also the human operators who their main job is, of course, many of them are automated with the diagnostic system, but still human operators need to use their manual pipetting or some multiplexed pipetting system, which is quite time-consuming, time-taking process, and also have quite a lot of risk of contamination for both operator and also for the samplers. So, and especially to use new technologies called the lab on a chip devices, which is tiny microelectronic devices integrating the microfluidic function comportment and the biosensors electrical measurement. And using these new devices, we still also need to have additional devices like a microfluidic syringe pump to be able to control very tiny amount of liquid volume transfer in between these devices and diagnostic system. So then the question arises here. So as you say, all of this with all of this makes this biological sample taking and diagnostics are remaining to be local laboratory facilities, the question arises: what could be the future alternative for this? So the microrobotic swimmers could do some part of sample handling jobs. For example, I called here microrobotic transporters. And the first example we have recently shown a solid sample transport by a tiny MEMS device. It's a resonating microrobotic swimmers, which we can deploy them in a quite with a lot of solid microparticles, and they can transport massively such a solid sample by fluidic manipulations. In addition to solid sample transport, liquid sample can also be transported by recently, for example, developed 3D microfractal pipette, which having inner cavity structures which can contain the liquid from liquid source samples, and by capillary force and deliver this the liquid sample to the, for example, hydrogel substrate. All can be done by capillary force, capillary effect. However, their current limitations are these operations are limited in single-phase environment, either in fully aquatic solution, liquid environment, or in dry environment. And the manipulations is either solid object or liquid samples, but not both of them. And their manufacturing cost and complexity still remaining to be the small challenges. And then I call this hard microrobotic transporters. The new direction could open with the soft microswimmers. And okay, here then we had to first look how we manufacture such a soft morphological transformable swimmer. Then in the current state of art, most of the work of soft morphological transformable structures has mainly been focusing to the limited manufacturing scale range, either in the micrometric structures or in millimetric structures. And in addition to be able to more enhancing the environmental adaptability, we can also program surface structures by microstructures. And this is currently limited by available technologies. So today, our work is to propose these multi-scale manufacturing approaches from micrometric to millimetric, and also further integrate this surface microstructuring capability. The device concept is shown in this slide. So these structures can self-deform their morphology in between cylindrical structures to the flat ribbon shaped structures by external global magnetic fields. And the device scale, as we say, with the current our optical setups and manufacturing system, we can fabricate from the scale between 385 micrometer to a few millimeter scale. And the thickness of this film is around 30 micrometer to 130 micrometer. The fabrication process is summarized here. First, we prepare the glass substrate with the micro spacers to define the thickness of the ribbon structures. And then we deposit magnetic particle slurry, which is composed of the magnetic microparticles and the soft UV curable resin. And then we have to program the magnetization, local magnetization. For example, here in the case with the self-deforming to cylindrical structures, we can magnetize in 3 compartments, on the left side and the middle part and the right side. So the UV reticulation is done sequentially on these 3 compartments. So first part, we do globally magnetize from the left side to the magnetic slurry, and then we exposure locally, UV exposure the first 1/3 part. And then once this part is fixed and reticulated, their manifestations, we do the second part of magnetization and reticulations by changing the magnetic field directions. And then by sequential UV reticulation, we can achieve this soft transform microstreamers. The manufacturing system consists of a UV projector, which is used to generate UV exposure pattern. And this pattern is optical, by using the optical zoom optical system, is focused to the sample stage. The sample stage is mounted on the 3-axis translation microstage. On the bottom of the sample stage, we place a 3-axis rotational magnet, which is used to change the magnetic field during the manufacturing. In addition to the self-deforming self-transformabilities, we can also program the surface microstructuring to the soft streamer. We do the same magnetic particle slurry, and then we, in this case, we pull down by the external magnetic field gradient on the bottom to the bottom directions, and the magnetic particles aligned to form tiny microspikes, which is the height of between the 56 to 83 micrometer. This helps us to reduce solid surface adhesion by reduce the surface contact area, and also it contributes to increase liquid absorption by increase the surface to volume ratio. And to see the morphology transformations, initially right after the fabrication, due to the built-in stress, it deformed to the cylindrical shape with the opening distance d. And by applying external magnetic field, for example, here in the downward, like globally, and these cylindrical structures become to the ribbon, flat ribbon structures. And by cutting and removing the magnetic field, it comes back to the cylindrical initial shape, and which, thanks due to the elastic property of these structures. And then these soft streamers can swim and can inside of liquid environment. Here, first is swimming. It's not swimming, it's rolling onto the substrate in liquid environment, which is useful to the robust motion. And also it can float and swim by three-dimensional, by external three-dimensional Helmholtz curve setups to generate the rotating magnetic field. For the morphology transformation, we use a bottom-placed electromagnet for the gradient magnet field have these morphology deformations, which is useful to grasp, for example, a solid object inside of a confined channels, liquid channels, and which can simulate their potential application to the biopsy or drug delivery. And then this can also transport the liquid samples from the red dye droplet, and it enter to the droplet, and it can mix and absorb this droplet by its solid microstructured surface, and it can transport this absorbed liquid to hydrogas substrate or to the other liquid droplet sources. And this shows when they transport this the left red dye to the water on the right side, it can have a mixing by the rotating streaming, and it can comes out of the droplet, and it can iterate these operations. So this feature by entering from dry and to wet environment, which is very important, but it's not easy to realize for the physical limitation of the surface stiction and friction, especially at the smaller scale. But thanks to this water absorbed and the microspikes, which we can have minimum surface stictions, and this operation can be freely made. And then this can, we can multiplex the two of the streamers with the two different liquid, for example, samples and the blue or red dye. And then we can transport each of them and then mix them to the target positions. This can be also programmed with different, multiple sources of liquid, and either by the 3 different colors, to prepare a necessary amount of samples with this system. And finally, I'm going to show the prepared samples can be transported to the paper here. In the paper can wet all the transported liquid, which is illustrating the potential application to the paper-based biochemical sensors. So then, to look at the environmental adaptability and sustainability, we had characterized the propulsion performance, and we measured the propulsion dynamics was reached up to 480 body lengths per second, and the propulsion force was around 18 micronewton, and pressure can generate 5.8 Pascal, which is 5 more times higher than wall shear stress in artery, which showing that such an environment, more harsh environment with the underflow, could also be considered for their future applications. And their manipulation of a solid object, for example, in a confined environment, this swimmer can transport and making a densely packing assembly, and to make more stable grasping, pick and place manipulation, we added 2 more arms. So it means this swimmer have 4 arms. We can grasp and transport this solid object. Finally, we tested for long-term conservation and more like brutal use afterwards, but even after the ultrasonifications. And afterwards, the swimmers survived without having a critical defect. And as we say, it's just something we can, even after drying, we can dry without having surface tension issue, and it can survive their operations. So this work was realized thanks to the collaboration between University of Tokyo and the CNRS, internal collaborations. And to summarize the talk, so we have proposed a soft microswimmer, swimming agent, but not only swimming, but all can go out of the liquid and move out of the liquid to be compared to multi-phase environment, which is important to also, we added soft transformability to be able to functional as grasping, solid sample manipulation, at the same time, also liquid sample manipulations. So thank you very much for your attentions, and yes.
Yeah, yes. Thank you so much.
Thank you very much.
Time. So thank you for this very nice talk and on the nice devices with some interesting technologies regarding minimum resources and the energy perhaps for the fabrication. So now it's open for question. Do some of the attendees have some question? I guess yes, plenty ones, no? So I may have some, and if people... oh, Paco?
Yes. Hello.
Yes, please? Yeah?
Yes.
Yeah, you.
I was wondering, like when you do the lithography, you need a magnet. You have nanoparticles in the resin, and you have a magnet to give them a polarization, non-magnetic polarization. That's it.
Yes. During the okay.
Yes.
Yeah.
So like how uniform needs to be the magnetic field in order to guarantee that these conformational shapes will be reliable.
Yes. Okay, so uniformity is important, but for the I didn't worry too much, because the field uniform, the zone of the magnetic field uniform zone was sufficiently enough large for the scale of these structures. So it's a few centimeter scale, and the local compartment part was a millimeter or 2 millimeter scale. And the uniformity is important, but the intensity is another important, because the soft this resist in viscous phase, as we still need to have quite strong magnetic reorientations, and this is another concern to properly orient the particles. Yeah, dipole.
Thank you.
Thank you.
Okay, thank you too. I guess we have another question from Du Young.
Hello, this is Du Young from Abdullah University. Thank you very much for your nice presentation. It was very impressive. I had just a question about the number of the swimmers. So all you have shown was a single micro swimmer. I was wondering if you have some idea about the multiple swimmers.
Yes. So the here in this work, in this paper, we only showed one single, mainly the single swimmers, and they're using sequentially. But then concerning your questions, it's also important to make a multiple swimmer and possibly selectively. So we showed here in the video 2 swimmers moving together. Here in this case is they moving globally, but also slightly selectively, not always the same way by the global magnetic field. And we are currently working on the localizing the field onto the control more close to the single swimmer scale. So we can extend currently going to 4 and the more numbers of swimmers. This will require the improvement of the external magnetic setups. Yes. Is it answering your question? Or?
Yes. Thank you very much.
Thank you.
Okay, thank you. I can see any other question, perhaps a short one related. Perhaps I can see that I can move quite easily, it seems, in water. Do you have some experience about some perhaps more viscous fluids or things like that? Is it able also?
Yes, and so here all the experiment was done basically the water solution, so viscosity was fixed to water, and but if we use the more viscous medium, let's say or even I don't know, the blood, or even more like more viscous medium, more biological fluid close, and this could the viscosity in fact is one of the major obstacles to change the environment is mostly at this scale is the stiction is getting stuck. So this swimmer thanks to the surface structures and liquid absorbed, it can have a lubrication effect between the solid substrate, and we didn't notice any critical stictions. That's it makes this operations. But to go to really viscous, we haven't really tested with a very viscous, but in the for example, operation can be dynamic can be slower, and as we showed, this dynamics was in water with a very high dynamics, and this force and the pressure can can overcome such a viscous limit.
Okay.
So that's I believe that we will not. Could be possible. Yes.
Okay. Thank you. So maybe there could be an issue also with the conductivity, electrical conductivity of liquid, but I guess we can discuss that in the break rooms. And now So thank you very much. Thank you and congratulations.
Thank you very much. Yes.
It's time now to turn to the next speaker. Thibault Delay is there.
Yeah, I'm here.
Okay, thank you. Hi. So during I will introduce you shortly. You can try to share your screen meanwhile, perhaps. So Thibault Delay has received the Master Science degree from the University of Louvain in Belgium in 2015, and you are now a PhD student at the Institute of Information and Communication Technologies, Electronics and Applied Mathematics, University of Louvain too. You was visiting international research student at the University of British Columbia, Canada during fall 2018, and your research topic is on highly sensitive and ultra low power MEMS pressure sensor based on silicon on insulator technology. So I let you start your talk now, please.
Thank you, Corinne. So good morning, everyone. I'm Thibault Delay, and I'm coming from the University of Louvain in Belgium. And today I will present you our work, bottom-up life cycle assessment of MEMS piezoresistive pressure sensors. As a small introduction, here is a prevision of the MEMS market made in 2017. And we see that MEMS market should rise tremendously. And in fact, it should double between 2016 and 2022. And we see that until 2018, MEMS pressure sensors were the biggest part of this market. And it should remain one of the biggest parts in the future. On the other hand, recent studies show that with advanced technologies come big impacts. Here we show the increase in energy demand and in greenhouse gases emission related to the advanced CMOS nodes. And the question that is coming with that is that if we are applying this kind of philosophy with the pressure sensors, will the newest pressure sensors be more impactful than the older ones? So in this presentation, I will first rapidly explain the MEMS piezoresistive pressure sensor basis of principle and process flows. Then I will present the bottom-up lifecycle assessment we made. And finally, I will discuss the impact regarding to the performance of the sensors. So let's go with the principles and process flows. So MEMS pressure sensors are tiny devices based on a silicon membrane on which are placed small resistors. Here, doped silicon resistors that are the resistors in red that will act as strain gauges. Here we can see the resistors that are placed on the edges of the membrane. And if we are looking at a cross-section view, we see that under the effect of a difference of pressure here between P plus and P minus, the silicon membrane will deflect, creating a deformation of the strain gauges that will create a modification of their electrical resistance. This is this electrical resistance that we will be able to read with an external system, and that will contain the pressure information. But how these sensors are made? So without going into details, they are manufactured inside microfabrication laboratories. We begin with, for example, a bulk silicon wafer, on which we apply a bunch of cleanings, lithographies, dopings, deposition, and so on, in order to obtain these doped silicon or polysilicon resistors on the front side of the wafer. And after that, we are releasing the membrane by etching of the substrate from the backside of the wafer. Different etching techniques exist. For example, we have the anisotropic wet etching with KOH or TMAH, or anisotropic dry etching, for example, the deep reactive ion etching with SF6. One of the main advantage of the anisotropic dry etching is the almost no slope sidewalls that allows, for example, reducing the area needed for the membrane release. Another variation of the process is to use silicon on insulator wafers with a buried oxide layer underneath the active silicon that can be used as a good edge stop layer. This allows for thinning the membrane down to 3 micrometer, since the bulk silicon struggle to allow for going below 10 micrometers. Coupled with dry etching, this also for allowing high precision membrane patterning from the backside, allowing for creating stress concentrators to increase the sensitivity. So in this study, we used 2 case studies. The first one is the work of Kumar and et al. Made in 2006, that is based on SOI substrate and wet etching. And the second case study is the work of Lee et al. In 2018. This is also based on SOI substrate, but with dry etching and membrane patterning. So we now go for the bottom-up life cycle assessment of the MEMS pressure sensors. And so the main objective of this study, in fact, there is 2 goals. It's to quantify the cumulated primary that is needed during the manufacturing of the MEMS pressure sensors. And also, we want to quantify the global warming potential of the greenhouse gases that are emitted during the MEMS pressure sensors manufacturing. About the perimeter of the study, when we talk about accumulated energy demand and global warming potential during the manufacturing process, we are in fact also including all the accumulated energy demand and global warming potential related to the raw materials and the chemicals needed for the manufacturing process. And so including the wafers, the gases, the etchants, and so on. And as a first milestone, we are focusing up to the front-end manufacturing, so just before the testing of the wafers. So we can say that we are doing kind of studies from cradle to front-end process. About the inventory model, so the CED and GWP are computed thanks to this formula that is including all the raw materials and the chemicals flows and energy intensities, and also the energy needed and associated with the electricity used during the manufacturing phase. And all the data that we are using come from previously generated life cycle inventories for CMOS processes. As a first result of these studies, we can clearly see that the major contribution, both for the accumulated energy demand and the global warming potential, is due to the silicon wafer production. And about the silicon wafer, we can see that the impact of the SOI wafer on the process, we see that it creates an increase of 20 and 10% respectively on the accumulated energy demand and the global warming potential for the wafer production. About the difference between Kumar and Lee's process, we see that Lee's process is slightly less energy demanding. There is a difference of 4% due to a reduced number of steps during the process. Since it is more global warming potential intensive, with an increase of 30% due to the use of dry etchings. So we can see it more clearly here on this graph, showing the details for the process steps impacts. Dry etching produce a huge amount of greenhouse gases. So about the impact of the membrane release, dry etching has a 7 times bigger global warming potential than the wet etching, mainly because it releases SF6 into the atmosphere, SF6, which is a gas with an extremely high global warming potential that is about 23,000 times bigger than the carbon dioxide. I will now discuss these results regarding the performances of the pressure sensors. For this purpose, we will use the mechanical figure of merit for pressure sensor, which is defined by their sensitivity divided by the membrane area. And using a reported previously reported state of the art, we can observe that SOI and dry etchings enable to reach thinner membranes. So they enable us to go at the left of the graph down to 3 micrometers, while membrane patterning represented with the diamond point here allows for increasing the sensitivity up to a factor of 6 at 10 micrometers membrane thickness. We also use this state-of-the-art to draw 2 experimental lines modeling the impact of the membrane thickness of the mechanical figure of merit, depending on the membrane patterning, membrane patterning or not. And so we use these 2 experimental lines to predict the best performances that are reachable depending on the technology mix. And we can see that going from bulk silicon with membrane released by wet etching to silicon on insulator substrate with membrane released by dry etching and membrane patterning allows for a 50-fold reduction of the area needed per sensitivity units. So this is a huge improvement. Sorry. Finally, using this last graph coupled with the result of the life cycle analysis, we computed the cumulated energy demand needed and the global warming potential implied per sensitivity units, depending on the technology mix. And we see that the improvement of the mechanical figure of merit thanks to the SOI and the dry etching and the patterning is way bigger than the increase in cumulated energy demand and the global warming potential per area that become totally marginal. So in conclusion, we show that major impacts in the cumulated energy demand and the global warming potential are coming from the substrate. There is an increase of 20 and 10% of the substrate cumulated energy demand and global warming potential. If you are using SOI substrate, about the membrane release steps, dry etching has 7 times bigger global warming potential than wet etching. And about impacts regarding performances, we saw that SOI substrate, dry etching, and membrane patterning allows for a 50-fold reduction of the area needed per sensitivity units. And these performances improvements supplement by far the impacts increases. And finally, we can advise 2 improvement tracks. The first one is trying to investigate new low global warming potential alternatives for SF6 for the silicon dry etching to reduce the release steps global warming potential. And then to analyze the reduction of yield that should come with a reduction of the wafer thickness in order to find the best compromises to reduce substrate impact as much as possible. Thank you for your attention. It's now time for a few questions.
Yeah, thank you very much, Thibaut. So very different topic compared to the previous talk. It's interesting to analyze the impact of technology in terms of energy and carbon footprint. I guess from what I remember of the submitted the preliminary paper that you have added some things related to the last conclusion, in fact, taking into account also the surface, the global things, in fact, and not only the environmental impact. And finally, it mitigates a little bit the conclusion compared to the first ones, if I remember well. So yeah. Anyway, so let's start with a few questions, perhaps within the attendee. We are perfectly in time. We have a few minutes for a question. Yeah, Yoshio, please.
Yes. Thank you very much. Yeah. Actually, it is honestly speaking, it is my first time to see life cycle analysis with MEMS. Yeah. Congratulations. Do you know other colleagues who are doing such works than you? So you are only the one.
So about MEMS, I have a colleague at UC Louvain who is doing life cycle analysis for quality water MEMS. But about MEMS, I don't know anyone else doing this. We have a lot of discussion with researchers about CMOS processes impacts, but not about
MEMS. So it is quite really new. Yes, I was very happy to be how to say Temuan, so a witness of news. Emida, yes.
Hello again.
Yes, sure.
You see me? Yes, you see me. I had a question about. It was very interesting. We are used to have lots of silicon devices in our hands, and we don't always think of the carbon footprint of these devices. One thing I was wondering is, well, it's a question I had, open question, about lifetime of these devices. Because, for example, if we might, let's say for a pressure sensor, we put it in a smartphone. We know that the smartphone has a lifetime of something like 1 year or maybe 2, but not more. Or if it's in an industrial process, it may have a lifetime of maybe 10 years or maybe more. So how do you have an idea of how to integrate that in your work?
Yeah, so it's really
very difficult.
And because it has a lot of variation in the use. So that's why for these studies, we only focused on the manufacturing process, because in fact, the active life of the silicon is really complicated to measure. So yeah, there is in fact, we can do it by maybe if you are looking at the share of the market, how much silicon is used for consumers, for industries, we can have an idea of the lifetime. As you mentioned, in the industries, maybe it will be 10 years. In the consumers, we can maybe say 2 years or maybe 3 years. And then by doing this kind of hypothesis, we can have a look at the mean lifetime of the silicon and maybe have an idea about that. But it's really complicated to have a really accurate answer to this question.
Okay, thank you. But indeed, I would not go into that, but I would be very much interested if you manage to integrate that in your work. It would be very, very interesting. Thank you very much for your presentation and for your answer.
Thank you, Emile. Just a last short question.
Okay, Patrick Poulichet from Essier. Do you hear me? Yes. Yeah. Okay, my question is about the gas SF6. And I discussed with some guy who work in the clean room at Essier, and they said that it's fixed in some material before to be released in the atmosphere. Do you confirm or not?
Yeah, so in fact, this is mandatory that you had to keep as much as possible SF6 inside the clean room manufacturer.
Okay.
But it's not possible to keep all the SF6. So in fact, in this study, we consider that 90% of the SF6 is kept inside the manufacturing. So only 10% of SF6 is released inside the atmosphere. For example, there are also other gases as NF3. And for this gas, it's mandatory to keep 95% inside the manufacturing. So there's rules about these different gases, and for SF6, it's 90%.
Thank you very much.
Welcome.
Thank you so much to all the people with the question and to Thibault. Sorry.
You're welcome.
So let's turn now to the third and last speaker for a short talk. I guess it has been recorded. Is that true?
See, hi.
Oh, okay. Okay, so I will introduce you, Adil. So Adil Arshad received his Bachelor of Science in Electrical Engineering from the Superior College La Jolle in 2016. You completed the Master Science degree in Electrical Engineering from Information Technology University of the Punjab in 2019. And your research interests include micro electromechanical systems, so MEMS, and low-cost biomedical sensors. Currently, you are working as a research assistant in College of Electrical and Mechanical Engineering, Rawalpindi. And
yes.
Let's go now to your recorded video and for a few minutes, and we will have.
Hi, I am Adil Arshad. My paper title is Brush Painting All Carbon Variable Dual Temperature and Strain Sensor for Human Health Monitoring. My co-authors are Mohammad Umaid Bukhari, Mohammad Qasim Mahmood, Mohammad Zubair, Dr. Kashif Fayaz from Department of Electrical Engineering, Information Technology, University of Punjab, Pakistan. In problem statement, healthcare facilities are difficult for remote areas. Rural communities are so far from big hospitals. Financial issues, geographic accessibility is also difficult to time manage. One solution of all these problems is wearable technology, which is low cost, portable, user friendly, highly flexible, and multifunctional. In our work, we have developed a temperature and strain sensor. Strain sensor is used for the detection of movement of human body parts, in which one is knee, elbow, wrist, and finger. Temperature sensor is observed on different temperature, on human body temperature and on room temperature. Material that are used for in the fabrication of sensor is one is sticky note paper, that is a substrate, as a substrate, paint brush, which is used for painting of electrode of strain, and temperature sensor, conductive paste, which is used for electrode fabrication, which is prepared by mixing of 5 gram powder of graphite and 1 ml ink of gel pen. Okay. Sensor design and fabrication. Sensor design and fabrication. Temperature sensor length is 50 mm, width is 5 mm, and strain sensor width is 2.5 mm, and separation between two fringes is 2 mm. Total size of sensor is 25 multiplied by 30 mm square. In figure, at first step, paper is shown. On the first step, on one side of the paper, a layout of strain sensor is drawn by a lead pencil. On another side of paper, a temperature sensor layout is has drawn, uh, and layout. A, a conductive paste is painted with the help of brush, as shown in step 3, like in step D and E. Operating principle of strain sensor is shown in figure A and B. In figure A dimension of strain sensor is shown, and in B, when strain is applied on sensor, then changing or occur in sensor are shown. Testing and result. Temperature sensor. Temperature sensor variation in resistance of temperature sensor corresponding to temperature. When temperature is increased, resistance of temperature sensor is decreased, as shown in figure. This due to its property of graphite. Sensitivity of temperature sensor is 0.651 kilo per centigrade. In the next figure, response of temperature sensor on body temperature and room temperature is shown. Room temperature resistance is 41 kilo and when job temperature sensor attached on human body, due to body temperature, resistance of temperature sensor is decreased, as shown, which is around 34-33 kilo. Testing of strain sensor. Response of strain sensor when attached on flat elbow, as shown in figure. When job strain sensor attached on flexed elbow, its capacitance is around 15 picofarad. When job elbow is extended, the capacitance of strain sensor is at 12 picofarad. In next figure, also strain sensor on flexed and extended is shown. When flexed, then capacitance of strain sensor is around 10 point something. When extended knee, then capacitance is at 9.5 something. In this strain sensor on wrist finger without attachment is when job figure is when job strain sensor is and without any strain, its capacitance is around 4. When job attached human body then capacitance is increased at 1. Pico. But capacitor when capacitance strain sensor is attached on finger, and due to further capacitance strain sensor is further. Here your temperature and are check of on temperature sensor. Uh, not of them strain I from body temperature. Binding effect on temperature is shown by band body up strain and temperature. The low cost variable human health trial method is used and temperature was like knee sensor on another.
Okay. Okay, thank you. We had some technical problem, I guess, with the sound, but we had the image at least. So I don't know. I guess we will have some question, perhaps regarding the repetition of some parts. I don't know. So thank you for that, Patrick. No, okay. So it was remaining from the last talk. Are there some questions in the audience? Okay, I will. You sure?
Yes. So thank you very much. Probably Sense Proud company is doing quite similar stuff. So printed electronics for the sensors in case of Japan, by the way. So my question is that you manually actually painted so the sensors, and I think there will be due to the slight difference, the capacity performance, so the capacitance may be changed. So how many samples do you have made, and have you got the same result, or it had distribution?
We sample 3 sample was tested, almost capacitance variations was same. There was no changing if conductive paste thickness and conductive paste carbon and ink gel pen is quantity is same, then there is no variation in during the drying.
Very interesting.
Yes.
Thank you.
Okay, thank you. Yeah, I guess you may have some variation between several devices, no? But that's sure that it can be either undertake a calibration step perhaps, or more reproducible way of depositing the ink with the carbon inside. You really had the same values? It's very surprising.
Yes, it can.
Okay.
It maintain carbon graphite and ink gel should be same in every moisture, in every conductive paste, and painting should be just single coat, not increase coating of painting. It can be.
Okay. 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 Any other question? Not yet. Can you explain the corner shape of the resistance for the temperature sensor rather than a classical serpentine pattern, perhaps? Did you talk about that?
Yes. I want just double strain and temperature sensor on same size of paper. So just for that length, we want length of 50 mm, just 30 mm in the length, and bend after 30 mm to 20 mm.
Okay, it is due to the final performance that you expected.
Yes.
Okay. Okay. Yeah, okay. I don't know if you talked about that in your paper. I read something related to a pair of 3 fingers for the capacitor. What is this 3 fingers pattern that you talked about in the paper that you submitted?
Yes.
Yeah.
Yeah.
So we had interdigitated structure with the 2 fingers, no?
in my capacitor there are 3 or 4 fingers.
Okay.
It's compact capacitor.
Okay, okay. It is not the unit pattern. Okay. Do we have some other question meanwhile? No? Okay. So I guess we are perfectly in time, and thank you so much everyone for attending or participating to this session. I guess it's an important issue both from technological and also societal concerns, in fact, and I really hope we will go further with such concerns. So thank you very much, and I let Pascal take the lead, perhaps, for the coffee and break rooms part.
Yes, Corinne, thank you for sharing this session and proposing to have such a session that was very interesting. So we will now split the audience between the different breakout rooms. So you can have the list here. So you have in breakout room number 1, Shaozi, then Robert Hanout, Thomas Arnoux, Guigwen Wang, Thibaut Delay, and Adil Arshad. And we will resume with the next session at 11.
A paper conducted by Munira Bengashir and my supervisor Ivan and Owen Gasha, and my co-worker Russell and Barnaby Bertelli, Department of Microelectronics and Electronics, University of Malta. So in this presentation, we will have introduction and the methodology. We go shortly to on the process description and design and switch design. Which is we have 2 types of the switch, the 3-state switch design and 2-state low voltage switch design, and then we will show our fabrication and results test, and then we go to the conclusion. So in this paper, the investigation of a mechanical contact type RF MEMS switch for VHF band applications. Different contact electrostatically actuated switches were analytically studied and simulated using Coventerware finite element modeling software. The switches were optimized for different parameters depending on the design geometry and the number of actuator comp fingers. This work is an extension to development of a tunable piezoelectric bulk acoustic wave resonators with the aim of achieving cost-effective tunability over a wide frequency range based on a switchable array of these resonators. The switches were fabricated on the same piezo MEMS process as the resonators. Both 2-state and 3-state switches were investigated. In the case of 2-state switch, simulated and experimental value of the actuated pole and voltage were found to be 14 and 17 volt respectively. So starting with the process description and the design, as you can see, this is a cross section of the process of the design. So we can see here the switch were fabricated using the piezoelectric MEMS technology, which is based mainly on the beginning of 10 micrometers SOI layer, the red one, bonded to 400 micrometer silicon handled wafer, the green one, the blue one. And then we have a 1 micro thick of aluminum nitride is deposited on the SOI layer, while a 1.02 aluminum chrome pad layer is available for electrical connection. You can see this in this cross section. I showed the switch. You can see this is the movable part of the switch, and this is the fixed part of the switch. And we can place the resonator nearby. The resonator body, how it's floating. There is a small, maybe it wasn't showed, the small anchor because it's very thin, so it's not showable here. Switch design. So the 2-state and the 3-state switches design were investigated, and a serpentine spring structure, which is optimized for a low lateral banded stiffness. A total of four serpentine springs are used 1 and 2 and 3, 4. The implemented spring design consists of a single anchor, you can see, and a total of 6 turns. You can see the movable electrode here, and then you have the signal line from both sides, and then we have the fixed electrodes. The switch design using finite element modeling simulations performed using Coventor-Ware Mimic, and parameters are listed here. If you see the actuation finger length, 120 micrometer, actuation finger width is 8, and actuation finger gap, GA, is 3.5. And then actuation finger overlap is 110, and spring length 146, spring width is 3, device SOI is 10, and then we say single finger gap is 3, and then, oops, sorry, we have the number of actuator fingers are 14 in the case of 3 states. Oops. I don't know what happened here. You can, is it clear, the presentation still? Sorry. Okay. So, yes. Okay.
Yes, it is okay. Please go ahead.
Okay.
Yeah.
So we can see the layout of the 3-design 2-state switch. So we optimized the actuation into movement in one direction, and this is the optimized 2-state switch with 82 fingers. So this is the actuation movement, and the simulation volt was achieved 14 volt, the pollen voltage, using Coventor co-solve. Yes, in this slide we show the maximum displacement versus the actuation voltage for the 14-finger comb actuator, 3-state, and 28-finger comb actuator, the 2-state switch. You can see here the fabricated micrograph. This is the micrograph picture of the fabricated 3-state switch with 14-finger comb finger. And here the micrograph of a low voltage optimized switch integrated with 2 piezoelectric bulk acoustic resonator. So you can see one is referring to the actuation voltage. Number 2 is showing the signal line. Number 3 is showing the springs, and then number 4 is the piezo MEMS resonator. Fabrication and results. So using the cascade, using the characterization was done using cascade probing station, where the actuation voltage was applied using tungsten cascade microtech probing needles, measuring the gaps before the switch and before the actuator, GS and GA, were compared to the designed dimensions. So there is a very small fraction of variation. So you can see the design is 3 micro and the measured is 3.1. The actuator gap was 3.5 and the measured 3.6. The required actuation voltage was found to be 17 volt in the case of 2-state switch. In figure 7 shows the switch in the on state. In the on state, the signal path was found to be equivalent to the capacitance of 220 femtofarad in series with a resistance of 6.4 kilo ohm. In this figure, we show the on state for the three-state switch, the type 3-state switch. You can see on the right side, it's on. With the required voltage found to be 19.3 volt for one side, and while the other side is in a deep off state, presenting. I can see it in the next coming video. I can play the video. I don't know if you see the slide clearly here. You see the slide clear? So I play the video. In conclusion, this paper presented an investigation into a feasibility of a contact type switch, which can be integrated with piezo resonators on the same piezo mounts process with the signal finger geometry illustrated in this work. The off-on signal coupling ratio is limited, therefore future work will be directed toward maximizing the signal contact area and the contact force by exploring more complex signal contact surface patterns. Further work will also consider the possibility of implementing a double throw switch to be able to switch between two frequency bands using the same switch die area. Thank you for your listening, and I am open to the questions.
Thank you very much.
Okay.
So do we have any questions? I have one, I think, hopefully. I need to see if people have their hands up. No, okay. Okay, Munira, thank you very much. So at the moment, with what you've got there, you weren't able to test changing the resonance of the piezo device so far. Is that correct? Is this because the change in the capacitance when you switch is too small?
Also, the bonding, I didn't bond the switches. You see, I tested using, so it was very sensitive to the surrounding. But next fabrication, I will bond every pad, so it will be much easier to test, I think.
Okay, hopefully. Yeah, yeah. You would need to have, would you need to have like RF probing as well if you were going to use it properly?
Yes, yeah.
Okay. Okay, great. So do we have any other questions?
Yes, I would like to have to ask a question about the fabrication. You are using did you fabricate? Do you have a clean room and fabricated it, or did you?
No, we used to MEMSCAP, but so yes, I send it. So I don't fabricate in the university. Yeah.
And all the process is made by MEMSCAP, or do you make a back end finishing or some steps in your?
No. Even the packaging, they do it for us. So
okay. Okay, thank you.
Thank you.
Oh, just one more question about this. How many chips do you have when you order fabrication?
They give us it's 10 per fabrication. If you need extra, you ask for more, but 10 the minimum 10 die. Yes.
Okay. And so the design you provide is GDS, or do you need
GDS? Yes.
GDS.
Yes.
Okay.
GDS. Yeah.
With the constraints,
you have to follow the process
the design rules and
design rules. Yes, the process design rules. Yeah.
And they have a design kit to use with Cadence, or can you use any?
I use Coventor. Yes.
Coventor.
Yes.
Oh yes. But they gave you they provided you with the design kit, or do you have guidelines and you need to?
You have to. There is a like a PDF file process. You have to follow the rules of the design, and then I mean you can use Cadence, you can use Coventor, and then you export it. The important thing that you will export it as a GDS file, and then there is a CDR checker. You do the check that if there is any variation before submission.
Yeah.
So okay.
Okay, because I'm not used to this MEMSCAP process, but I used to work with other founders, and they provided a design kit with some software piece for Cadence that was checking and preparing everything, but it was with Cadence only. You need to have the Cadence license.
Yes, we have Coventor license in the university.
Yeah, okay.
Yes.
Okay, thank you very much.
Thank you. Appreciate it.
Okay, we have another couple of minutes. Oh, I think my camera is frozen, which makes it look kind of odd what I'm doing. I was going to ask one more thing about about the on-state signal path was 22 femtofarads in series with 64 kilo ohms. So there is a conduction path in there as well, right? Through the signal.
Yeah, in fact, you are talking about the on-state here in the two-state switch type. Yes. Can you repeat your question, please?
So where's the resistance come from? Is there actually a contact between the fingers?
Yes, you can see the switch here with the arrow. So this is there is a contact here. When I enlarge it, I found it very clear. There is a contact between the. In fact, in fact, maybe. Because I don't know what happened to my presentation, but I was planning to explain the on-off movement. So the forward movement, it will be 3 micro. That's why we gave 3 micro distance, but the signal gap, we call it. So it was that the total movement of the signal, while the actuator, when moving upward, we gave it 3.5 in the design. So it doesn't contact, so it doesn't short. The movable electrode will not short. So we only guarantee the contact on the signal line. So that's why we made the gap in the signal line smaller than the actuator gap. We call it GA, and the GS is the signal gap. So, and the total movement from the other side in the case of 3-state, it will be 6.5 upward, So that's why it goes on the deep off, we call it. So making the contact, I measured with respect to ground the RS and CS for the signal line, and that's what I found when they're on state.
Okay. And so what were you aiming for in terms of capacitance and resistance in the signal path for the application?
Well, I'm aiming because my resonator is working on the 60 megahertz. So the premier design for this type of switch, because it was applied using the SOI MOMS technology, the previous, let's say, piezo MOMS is based on SOI MOMS technology. So the difference is only on the thickness of the layers, and the type of piezoelectric as well. But because I was designing my resonators, they were designed using the piezo MOMS technology, and now I learned about this technology on the design rules and everything. So to have eventually to have a switchable array between 2 bands of frequency. And we thought about its low cost. Eventually, we will achieve having the switch and the resonators in the same die. So that's our aim. And that's why it's the first time to use the piezo MOMS technology to test this technology on this design, because having a 3 micrometer let's say gap, it's it's amazing. So it came very clear for us when we tested under the microscope, and so that's why achieving low cost mainly. So that's the aim, and have wider tunability range, of course. Yes.
And then maybe we should probably move on, but maybe just one question to think about is I don't know whether you looked at, does the piezo MOMS have sort of design rules or sort of standard transmission lines, things like that for these frequencies in the, does it enable you to sort of send these signals at these frequencies reliably?
Yeah, because if I understand you well,
it's designed for that, is it?
Yeah. So I worked so far to like 60 plus megahertz. So I don't know if it's achievable if I understand you well. So you're talking about a higher range of frequency, you mean, using this technology, or?
Yeah.
Yes, okay. I expect. Yes, I think yes.
Okay, great. Okay, thank you very much. That's been great.
Thank you very much.
So we will move on to the next paper in this session, and so this paper and the next one will both be presented by Abdulkarim Talbi, who's a senior member of the IEEE and received the MS degree in plasmas, optics, and electronics from Metz University, France in 1999, and the PhD degree in microsystems from the Henri Poincaré University in Nancy, France in 2003. In 2004, he joined the Central Lille and the Institute of Electronics, Microelectronics and Nanotechnology as a postdoctoral researcher. Since 2006, he's been an associate professor and then also a full professor at Central Lille Institute since 2018. And his research interests include physics, design, elaboration, and integration of multi-physics micro-nanosystems for sensors applications, phononic and photonic devices and straintronic devices, including acoustic wave and magnetoelectric technology, and thermal flow sensors. He's a co-author of more than 110 publications in top-tier journals and conferences, and he is the co-inventor of 5 patents. So I believe the original presenter is not able to do this first talk, and then Abdulkarim was going to present the next one anyway.
Yeah,
okay, so
exactly.
Yeah.
Thank you.
Okay.
Thank you, Chairman. And
thank you.
Hi, everyone. As the chair said, my colleague is not able to present because of medical reasons, and I will present for him. And I hope that I will transmit the complete information about the work. Just the paper report on the design of solid fluid acoustic sensors based on phonoresonance, and the work is made in collaboration between LPMR from Morocco, also AMN from Lille, and GPA from Russia. Short introduction, just to understand. We know that sensor based on wave phenomena, if we want to increase the sensitivity, we need to confine wave within the sensitive area. Also, we need to obtain high quality factor of resonance if in the case of resonator design. The proposed design to achieve this UC generally is based on waveguide and resonator. During the last 4 decades for photonics, there is a lot of works based on bandgap materials to improve the performance of such kind of devices, all inspired from semiconductor theory. And during the last 2 decades, the same effort was made to apply this on acoustic and also magnonic and electron through plasmonic crystal, for example. And this raised to crystal that we call photonic, phononic, magnonic, plasmonic, and others. In our case, we are inspired again from quantum mechanics, and we propose in this presentation to investigate the potential of bond in the continuum mode to design its preliminary study, bio or electromechanical chemical sensors. To define more what is bond in continuum modes, just I will take this figure that we can see there the spectrum as a function of frequency. As we know in a spectrum, we can identify a lot of discrete resonance frequency, and we are able to classify this resonance in 4 kinds in our case. I will start from the bottom, which is something that is regular, and we know it. It's the case of particle inside a well potential. We can obtain some bond state, the equivalent of bonded electron, for example, in atoms. And after, if we see outside the well potential, we will see that we call extended state. Resonance LICO mode is kind of resonance that radiate to bulk or to surrounding media. And finally, on the top, we see a kind of resonance that report on bond in the continuum state, which is a mode that is in the continuum, but don't radiate. There is no leakage to surrounding media. We will see in this presentation the different mechanisms to obtain such kind of bond in continuum state using symmetry protected mode. Also, there is another mechanism that is based on Fabry-Perot resonance. The advantage of such kind of such mode, it means that if we are exactly at the level of the frequency, the quality factor will become infinite. And only by changing some parameters of the system, the factor quality will decrease. It means that there is no dependence of quality factor on the surrounding media. It depends only on the intrinsic properties of the resonator. There is in photonic system, there is a lot of works, both experimentally and theoretically, but in acoustic, only a few years ago, we start to interest in such kind of resonance. There is a few publications, we have here the reference, and we are the first to present experimental, both theoretical and experimental result, and we published this just this year. The structure that we investigate to put out this phenomena is simple device. It consists of a plexiglass plate embedded in liquid, if we consider only solid layer. And the second configuration consists of two solid layers embedded on the liquid. With this configuration, we show the existence of this kind of bond in continuum state. And we show both the two mechanisms to create such a resonance. I will show you the experimental validation of this assumption. And I will also discuss how we can use the triple layer structure to design acoustic sensors. Just small, I will not go in depth to explain theoretical. You should to trust green function formalism to understand how we can obtain that. Just the transmission is obtained from green function, is written by the ratio between two set of parameters. All the parameters depend on the layer properties, but also on the surrounding media through the F0 parameters. If we consider, if we see when the transmission is equal to 0, it means that this term is equal to 0, and we replace this term inside, we will find the eigenvalue of the solid layers. In normal incidence, this is given by the simple formula that we know for simple single layer, the velocity divided by twice thickness of the layer, thickness of the layers. But if we are in oblique incidence, the eigen frequency depend on the velocity of the on the parameters of the solid layers, longitudinal velocity and transverse velocity. And here, the condition to obtain this bond state in continuum is we should obtain eigenvalue of the single layer, but also zero of the coefficient transmission. And you will say that if we have 0 in this term and we have 0 in this term, then we have some indefinite limit. But you should know that we can simplify generally if you consider simple function a that multiply x squared by x. We have also 0 by 0 if the limit go to 0, but the limit is not indefinite. It means that the transmission will be finite. And if you need more information about the calculation, you can find that in the paper. Now let us focus on this graph that represent the transmission through the solid layer for different angle of incidence. The black dot correspond to a symmetric mode eigenvalue of the solid layer. The blue scale dot correspond to the antisymmetric mode, and the white dot correspond to the zero transmission coefficient, the position of zero transmission coefficient. When the eigenvalue of the plate intersect zero transmission, we will create the resonance that we call bond in continuum state resonance. And if we are at normal incident, we have exactly the same. In this case, this can be explained only by that. You know that in fluid, we have both compressive and transverse wave. In solid layer, we have transverse and longitudinal. and the transverse is a diff mode. But if we change slowly the angle of incidence, we will see also the transverse in the transmission. The experimental setup is simple setup. Aquarium with just plate plus inside the aquarium. We have a transducer, emitter and receptor, and a network analyzer. Here we have the response of the transducer of the system without a solid plate, is the bandwidth of our emitter receptor. And the experiment and theoretical was also validated using COMSOL multiphysics. For that, only just to see that a green function model, we use infinite emitter and receiver. In experiment, we have finite size transducer. Just we check that our condition for experimental and model can match very well. This is checked using COMSOL multiphysics because we simulate exactly the same size of aquarium. And here we see the comparison between the theoretical result and experimental result. We can see here in the left the graph that represent the transmission and the different point coming from experimental and theoretical. We can identify by 1, 2, 3 the different position of big state, but that is interesting. We can focus on the right curve. We can see when we are at incidence of 23 degrees, we have the red and blue one are theoretical and experiment. The green one is the theoretical without absorption. We see the operation of resonance. We increase the angle of incidence until this resonance disappears. But the eigenstate value of the layer remain at the same frequency. Now, if we go from other side, we will see the apparition of the resonance. It means that just by changing the angle of incidence, we go from resonance to non-resonance to resonance again. This it will be more clear when we use the case of 3 layers. The theoretical model is exactly the same. The condition to excite this resonance is the same, just to get the zero transmission and to get the eigenvalue of the system. The resonator in this case is composed of solid, fluid, and solid. And we have all the eigenvalue of the system. And when the eigenvalue intersect the zero transmission, we obtain the bond state in continuum. We have exactly the same result, just we can focus on the transmission versus frequency spectra, and we see here exactly the same phenomena. At 26.5, we have the resonance and is Fano resonance. At 33, we have the big state. It means that we don't have, we have the zero transmission. Normally, we have a Dirac response for the peak, but the width is 0 when we don't use absorption. And when we go to the incidence of wave 34.9, the resonance go to the other side of the big state. Now we will focus on this Fano resonance. If we look at just on the localization of the energy of this mode inside the structure, we will see that all the energy is localized inside the liquid, the central liquid layers. It means that if we change the properties of the sensing layers, of these liquid layers, we will change the position of Fano resonance. We can also play on a lot of parameters, angle incidence, the thickness of the layers, and other parameters. And you can see here the response. The blue one we see when we are exactly at the angle incidence with big state, left and right of the big states. This configuration was used to design the sensors. If we see here, we take just the configuration with given geometry to start from 0% when we have only liquid. We add albumin concentration, and we see that directly the resonance upper. And when we increase the concentration, the frequency shift to high frequency, and the width of the resonance increase. And we have sensitivity and the quality factor is present maximum value near the big state. We can do exactly, in this case, we play on the concentration to move all the resonance. We can also play on other parameters. Here we fix the concentration and we play on the thickness of the liquid layers. We can also move the resonance. This means that we can choose the concentration, one operating point, and we can fix this point, and we can introduce change of concentration, and we can take advantage from the quality factor near near the targeted concentration. The sensitivity remain constant, but this is normal because we have exactly the way the mode, the resonance is completely localized in the inside the thin inside the liquid layers. We can also play on the we can also fix the layer and angle of incidence, and we can change the concentration. It's exactly the same parameter. We can move a lot of parameters. And finally, we can also change the angle of incidence and to put the resonance as we want to exactly solve, for example, target large dynamic of concentration. We can both sense low concentration, but also high concentration, because the position of big state can be controlled by several ways. Just to conclude, we have investigated theoretically and experimentally the existence of bond in continuum state and final resonance in sample structure, single solid layer, but also triple layer. Theoretical and experimental match very well. We also investigated the potential of this resonance mode in acoustic to design sensors. And for the next step, we will try to perform experimental for the sensing design, but also to try to test solid layer with low propagation loss. In our case, plexiglass is present in high loss, and try to transpose the design to nanoscale using surface and bulk acoustic. Thanks for your attention.
Great, thank you. That's really interesting. I've never come across this stuff before, so it's very interesting to see. So, do we have any questions before I try and ask something? Please put your hands up. Otherwise, I'll start. Do you see whether or not you could kind of start to put this into a microfluidic system so that your sensor becomes like a channel, or does it need to be quite a wide sort of structure to be able to do this, a sheet in a tank? How do you shrink this stuff down into making it into a sensor, do you think?
I don't hear very well the question.
Okay. Could you make your triple layer system with it being a micro channel or something like that you can flow material through to look at changes in the material?
Exactly. We need to understand. In this case, we perform the experimentation in the electrosonic regime. It means that the thickness of all layer is in the millimetric scale. The problem, if we go to macro scale, we should to work at high frequency. It means that we should to work at high frequency, but in this case, it means that we should to move to another kind of waves, not only bulk waves, but we should to go to something like surface wave or things. But for me, it's feasible, but we need to understand exactly how to adapt the design, because this works very well at low frequency because we have no constraint to assemble all the plates. But I think designing macro scale similar device, but in macro scale we need more. I think more thinking, more effort. It's not completely evident to go from one design to another design. I agree.
Okay. I mean, I may be also thinking, is it the same if you've got kind of like a 1D system, right? You've got this sheet that you're putting the signals through. If you went to a channel, does that change the way that you have to do the geometry of the excitation and the measurement? maybe.
But yeah, just to precise in this case, for example, for the triple layer, the quality factor, the resonance is inside the liquid layer, but the quality factor doesn't depend on the liquid layer. It depends only on the solid layer. And we show only because in our case we use plexiglass. I think if we use something like quartz substrate, but I know that is more. We need more money to buy quartz at this scale. But it can work more better in terms of quality factor.
Okay. Also, you need to be able to control the angle of the signal as well.
We don't need. We can fix the angle at the beginning if we want. Just we can choose the good angle to get this peak state, and after, when we introduce the concentration, when we modify the liquid layer, the resonance will upper.
Okay.
Even if we start from the big state, if we add the concentration, the resonance will upper.
Yeah, sorry, I'm looking at the figures in the paper, and yeah. So if you change the angle, you sort of change the resolution of the peaks, depending on the concentration. Yeah. Okay. Yeah.
It means that we have a lot of a set of parameters on which we can play to choose our operating point. It can be concentration, it can be thickness, it can be angle. We have a set of parameters to do that.
Okay.
But every time we can choose these parameters to be in the region where the quality factor is very high. It means that near the big state.
Okay, fantastic. So do we have any other questions for anybody else? I'm afraid I'm no good at the theoretical side of this. I just want to look at the practical. How do you make these things work? Okay, if we don't have any other questions, maybe we can move on to your the next paper, which is Abdelkrim again.
I will share the next.
Okay, thank you.
Okay. It's just in this paper we will present. It means that in the aim is exactly similar to the previous presentation because we want to improve the sensitivity of sensors, but in this case, just by introducing the surface phononic crystal. Then the title is Temperature Sensitivity of Surface Phononic Crystal MOID based on nickel pillars array deposited on lithium nubat. I will start by a short introduction to present the objective, but also just to present a short overview on phononic crystal to present the band gap mechanism, wave involved in phononic crystal, and the way we choose pillars. And after I present the result, the band diagram calculation and analysis of such band diagram, and discussion of surface mode, and finally temperature sensitivity. And at the end, I will show you the experimental result on this kind of device. And I finish by conclusion. Just in this, the objective of the study, as I said before, is to investigate the surface phononic crystal that can be used to control the properties of surface acoustic wave, and to use this this concept of phononic band gap to improve the performance and functionality of surface acoustic wave device-based sensors, particularly sensitivity and the limit of detection by playing on the quality factor of the system. Just to very short, phononic band gap correspond to some range of wavelength or frequency within which elastic wave cannot propagate through the structure. And we can see this in this band diagram. we have the frequency here, and the wavelength, and the different symmetry of the crystal. And we can see the zone in color that correspond to forbidden frequency. It means that any frequency cannot propagate in this zone. We have two mechanisms to obtain such band gap. First one is the well-known one, Bragg laws, where the materials, generally we use some nanostructured materials. In that case, the frequency is defined directly by the periodicity of the nanostructured materials. But the interesting one is the second mechanism, where we interact acoustic wave with eigenvalue of a given resonator. In such case, we have some new gap that open and that we call a gap of hybridization. It means that here we have interaction of the resonator with coming wave. And in that case, the frequency of the central frequency depend principally on the size of the resonator that we introduce on the system. Various waves can be used in phononic crystal, and previous work report on that. Bulk waves, both in micro scale, but also in macro scale. We know completely the first application for 1D phononic crystal is film bulk acoustic wave resonator, is well known, or solid mounted resonator. We can also integrate phononic crystal with Rayleigh wave. We can use hole inside substrate and interaction of wave with such kind of periodic structure. We can combine with lump wave, bath hole, also with low wave that are shear, generally are shear wave, and for Rayleigh wave is sagittal wave. Bath wave can be combined with phononic crystal. In this case, I present only the case of hole inside hole or some increasing inside materials. And here is just hole, and also periodic hole inside materials. But we can use all three pillars. There is a lot of works. I don't present all the literature, but just to see, we can use also some other geometry on the surface of such kind of device. This is our aim, is to investigate pillar-based phononic crystal. Why we chose pillar in comparison to hole-based phononic crystal, just because pillar can store mechanical energy in local space. We can also avoid the limitation of the host material techniques. For example, hole inside lithium nubat is very difficult to obtain. In that case, we add matter on the top of the substrate. Also, because pillar, we can play the frequency of resonance or the gap of hybridization can be controlled by playing on the shape of pillar, but also on the geometrical parameters of pillars. How to calculate the properties of such bond of such phononic crystal? Well, we start from dynamic equation combined with constitutive equation for the piezoelectric materials that relay stress and deformation and electric field, and from the other part, electrical displacement, electric field, and the deformation. This equation, all these equations are implemented in COMSOL multiphysics commercial software, and we consider only, because we have periodic system, we consider only Brillouin zone, and we can work in the along the high symmetry direction in the Brillouin zone. This is the geometry of the unit cell used for calculation. We use only one cell because we suppose that our phononic crystal is infinite, and we apply periodic condition on each side of the cell, and we calculate the frequency as a function of wavelength by choosing the different direction in the irreductible Brillouin zone. The result of this band diagram is shown on this figure. We can see frequency, and on the axis we can see all the direction symmetry of the Brillouin zone. And we can see here that we can identify two band gap here, and the second band gap here. The blue curves correspond to the surface mode, and the gray zone correspond to the radiative zone or bulk zone. The delimitation between the two zones is defined by the low velocity mode present in the structure. In our case, this is the Rayleigh wave, is the small velocity present in the substrate. But it can be also, for example, shear transverse bulk wave that can delimit the bulk wave and surface wave. And if we see the mode are labeled from 1 to 6, if we see the shape deformation of this mode, we can see that mode 1 is bonding mode, the mode 3 compressive mode, and the other mode tensile and some mixed mode. But for all this mode, the deformation is localized in the pillars. We investigate the same, but now by changing the lattice symmetry. For the first, just before I present the square lattice, but we investigate also the triangular lattice, and we rotate by 90 degrees the crystal to get the lattice that we call Y lattice, X lattice. It's exactly the same crystal, just we rotate on the surface of the substrate the crystal by 90 degrees. Here we have the Venn diagram for all. Just one thing we can extract from this result. If we compare all this Venn diagram, if we see the square structure and triangular Y structure, we can see that we have exactly the same Venn diagram. And you can see from this scheme of the phononic crystal that we have parallel line, and this give us exactly the same result. But when we see the triangular X, the wave doesn't see parallel line, but some line like zigzag of line, and this modify completely the interaction of wave with the phononic crystal. And we can see this, for example, just for mode 1 and mode 2. For the square, we have the two bonding mode along X direction, along Y direction. And for triangular X, we have some elliptic polarization of the bonding mode. And for triangular Y, we have exactly the same polarization of pillar than square mode. And we can see for the other shape, for the other mode. Just from this analysis, we can see if there is some effect on the sensitivity to any physical parameters. In our case, we choose the temperature. The model is changed. Just we introduce the stiffness parameters and density as a function of temperature, and we calculate the eigenvalue as a function of temperature. And here we plot the coefficient, the temperature coefficient of frequency versus frequency. It means that for each mode at different frequency, and we can see that when we are at 16, for example, 60 megahertz here, it means that the propagation is in lithium niobate directly. But when we are near 120 megahertz, the propagation is the mode is localized inside pillar. For that reason, we don't have the same sensitivity here and there. And if we see the square phononic crystal and triangular Y, we have exactly the same sensitivity. However, if we see the triangular X phononic crystal, the sensitivity around the resonance is not the same. Even the crystal is exactly the same, just the distribution of pillar on the surface define the sensitivity. This is one, I think, one of results that is really show the potential application of phononic crystal to improve the sensitivity if we chose the good configuration. We fabricate the device. The process is described here. Just we start by electrode to excite and for emitter and receiver. And after we deposit some photoresist, some silicon oxide, just small layer. And after titanium and gold thin layer, 20 nanometers. And we perform after photolithography with thicker photoresist, and we electroplate nickel after. After we etch everything to get only pillar on the surface. this is the same image of fabricated device. And here is the zoom on the pillar, on the square pillars. Just I give the response of the transducer, because to investigate such kind of device, we need a wide bandwidth transducer, and we design specific transducer to get wide bandwidth by using two kinds of transducer. Dispersive one, the wavelength vary along the direction of propagation, and slanted one, the wavelength vary laterally. And here we have the principal obtained the result. Is the normalized transmission versus frequency for square lattice. And here we have the normalized transmission versus frequency for triangular and X and Y. We can see, as we showed just before, that square and triangular Y are similar in response. However, the triangular X is not similar, and give us information about coupling of pillar on the top surface of lithium nubat. And now, if we test, and we can see that the propagation is inside lithium nubat, and when we go there, the resonance is confined inside the pillars. If now just we take in the network analyzer frequency in this region, we will find the comparative coefficient of frequency of lithium nubat without pillars. If we consider this position, we will find the comparative coefficient frequency of pillars and not of lithium nubat. In conclusion, we show in this presentation the investigation of surface phononic crystal deposited on lithium nubat, and we show that we put out the existence of band gap, the existence of surface mode. We also demonstrate that the temperature sensitivity of surface mode can depend on the design of the phononic crystal, in this case on the lattice symmetry, and we demonstrate all this theoretical result experimentally, both transmission, both the measurement of surface mode, but also the analysis of the temperature sensitivity of surface mode. Thank you for your attention.
Okay, thank you very much, Abdelkrim. That was again really interesting. There's lots going on there. I was going to ask about the arrangement of the lithium niobate and how much like the orientation of that matters. I don't know if that is included in the simulations as well.
Yeah, it means that the crystallographic cut, it means that the face of the nubat, we introduce all the crystallography properties of lithium nubat. It means that we play, is introduced just by changing the, the properties is defined in tensor, and just we rotate the tensor to get the simple rotation of the matrix.
Okay, so do we have any questions? I'm afraid I'm going past my knowledge here, so asking sensible questions is kind of difficult. Otherwise, I think we can.
Maybe Corinne.
Yeah, maybe.
Oh, sorry, Corinne. Yes.
Sorry, I didn't find the.
You put thumbs up. Sorry, I didn't see that. Yeah.
Thank you, Karim. Yeah, it's always very difficult to have a good theoretical background for me, but it's also always very interesting. Just a short question: is it quite easy to explain why the sensitivity, for example, is changed with the specific pillars organization or not? Do we have some ways to explain that, not going too far into the equations? And
no, without equation, just because just if you see because generally we see just the wave is localized inside the pillars. This is the same for all the configurations, square and triangular, both X and Y. But generally, if I will just maybe answer directly, if you consider, for example, Rayleigh wave and shear wave, love waves, they don't have the same sensitivity. Yeah. They are both surface wave. In this case, we can, and the difference between Rayleigh and shear wave is the polarization of the wave. In this case, it's exactly the same. If you see in the case of triangular X, the polarization of the mode is not the same than in the Y direction. And this explains just very easy the difference. If we don't have the same polarization, it means that we don't, the dispersion curves is not the same. You can see it also from these curves. You see the difference between the dispersion curves there and there. And I think you know that in the sensitivity depend on the group velocity, and the group velocity at this region is not the same. I think you have some formula in mass sensitivity for low waves when group velocity upper in the denominator. Is exactly the same here. The group velocity will upper in the denominator, and because here is very small than there, or sometimes become negative, then the sensitivity become higher for the triangular X.
Yeah, true. Thank you.
Okay, great. Thank you for the question, Corinne. Okay, I think we'll maybe, I think I'm out of time for this talk, so we'll move on to the next paper in this session, which is, oh, sorry, Zoom is being odd. It keeps moving things around, so I keep losing things. So paper 7 is vibrational characterization of bulk micromachined titanium membranes, and that will be presented. Oh, I think we have a video recording from Gwenel Becon, who obtained his PhD last May from the University Paris-Saclay. He's now being employed by the company Mystics SAS, sharing his time between the company and its partner laboratory, the Center of Nanosciences and Nanotechnology, which is now part of the University of Paris-Saclay. And the research topics are focused on MEMS out of bulk titanium. So I believe the speaker is here to answer questions afterwards, or in the session in the breakout rooms after the session. So Pascal, please go ahead and play the video.
Good morning, everyone. My name is Gwenel Becon, and today I'm glad to share with you the results of our project. My presentation is entitled Mechanical Characterization of Bulk Micromachined Titanium Membrane by Microbending and by Vibrometry. First, let's have a glance on the use of titanium in the industry. From the end of the Second World War, titanium has been widely used in a variety of industrial branches, such as in medical implantable devices. Titanium is indeed one of the most biocompatible materials that exist. It is also resistant to corrosion, which makes it useful for applications in harsh medium, such as application in deep sea water. As titanium is robust and light, it can be found also in the motors of airplanes. And so all these devices for this application have been enabled by the use of steps of forming of titanium. But these techniques and these steps have a major drawback. It has a limited resolution, and some useful miniaturized systems were not possible to manufacture or to achieve with these current technologies. In the past years, recent developments have been made to try to overcome these limitations of resolution. The strategy which was used was to transpose some microfabrication techniques from the silicon industry and to apply them to titanium. One of the biggest milestones which was achieved was the development of deep reactive ion etching techniques to titanium, as Rina Curie introduced you yesterday morning in her presentation. But it is not that easy, because you are changing your material, and only a few teams in the world managed to use this technique of deep reactive ion etching to develop their own MEMS out of bulk titanium, and so presented on this slide. So the team which fabricated these MEMS are located in California, in the US. And so our goal in this project is to create a whole new branch of MEMS out of bulk titanium. And in this talk, we will focus our speech more on pressure sensor or microvalves. So at the last session of DTIP, I presented to you the design of the pressure sensor with a titanium transducer, which is a capacitive pressure transducer, okay, which is composed of two parts. The first one is a titanium membrane, which is sensitive to pressure, and it will deflect when pressure is applied here, and it gets closer, this membrane gets closer to its counter electrode here. And it will induce a change of capacities. So here you have the wafer one, so that's our titanium membrane. And you have a titanium counter electrode here, which is isolated from the rest of the substrate by a titanium dioxide ring, which is an isolant. And the two wafers are then bonded together to form the pressure sensor. So here I'm going to talk a little bit more about the membranes. And here are some pictures of the obtained membranes. And that's how we manage to fabricate them. So it all starts with a titanium wafer. Then you deposit some thin chromium copper layer by thin deposition. You pattern some photoresist on it to use it to perform a step of electrolytic growth to create a nickel hard mask. Then you remove this photoresist, and you can finally use the step of deep reactive ion etching. Finally, you use a wet etching step to remove the nickel hard mask. And so, the obtained membranes were characterized by microbending and by vibrometry. But if we take a look closer on the membrane, we can see that the membrane is not of uniform thickness, but it can be modeled by an elliptic shape. Yeah. This model was already used for previous results obtained for bulk testing with success. Lots of success. The microbending techniques, a punch at the center of the membrane will apply a deflection and monitor the force which was applied to perform this displacement. We could apply up to 10 millimeters at the center of the membrane. Configurations were investigated. First, the chip with the membrane was simply placed on a support with a hole. Then, the membrane was glued to its support. Those are two mechanical conditions which are not the same. Timoshenko described the behavior of a clamped circular membrane when a load was applied at its center. The maximal deflection is depending on the membrane radius and on the shape of the membrane with the plate conformity. This analytical model is only valid for membrane with uniform thickness. That's why, to predict the results we will obtain from our microbending technique, we decided to model our membrane with a elliptic shape using a finite element analysis depicted here. Here, you have the force against deflection curves that we obtained from the two configurations. So for each configuration, we perform a reference measurement outside of the membrane. From these curves, we extracted the stiffness with a linear fit at the beginning of the curve. And it has been seen that the model fits pretty well the experimental data. So here you have the two results from the two configurations, and here you have the models, the results that we obtained from the simulations. So the difference between the two experiments is not completely explained. It could be due to induced stress because of the gluing. The uncertainty on the real thickness of the membrane can also explain the difference between the experiments and the finite element analysis. Work is still in progress to better understand the effect of tip gluing to extract both the elastic constant and the stress within the membranes. In microbending, were also compared qualitatively to previously obtained both test results for the same tip. What can be seen is that there is a good agreement between the previous results and the new ones. Indeed, in both cases, a non-linearity becomes significant at around 4 microns of deflection, which shows a good consistency of the experiments. We also performed a vibrometry experiment on two membranes. The behavior of a clump membrane with an out-of-plane excitation is given by this wave equation, where T is the radial tension. The result of this equation are involving Bessel functions, and it can be proven that if excited at some given frequency, given here, the membrane will enter in a resonance mode. Again, these equations are valid only for membranes with uniform thicknesses. What we can see is that the resonance frequency depends on the stress, here, sigma, of the membranes. Similarly, with the microbending, we simulated by finite element analysis the elliptic shape of the membrane to quantify the impact of the elliptic profile on the mechanical dynamic behavior. For that purpose, we perform vibrometry to identify the resonance frequencies of two membranes. We use a time average interferometry with phase shifting demodulation technique, and so it is working like a Michelson interferometer. Part of the initial beam is sent to a sample which is placed on a TZT disk and will be our AC mechanical source. And the other part is sent to a mirror and gets reflected and goes back to the beam splitter. So both beams can recombine and form fringes on the beam splitter, and the resulting interferogram is collected by a CCD camera. So two membranes, which were 2.4 millimeter in diameter, were investigated with this study. So here you have two images of the fringes which could be obtained with a mechanical source off or on. When you are approaching the resonance frequency, the fringes becomes blurry as the membrane begins to vibrate. With this blurriness, it becomes possible to identify with precision the frequency, the resonance frequency, using the contrast image from the image of fringes. We were able to identify some of the first modes of the membranes. We put in this player both the experimental results and the simulation results. From the simulation, we can learn that if the electric profile is important, the ratio of the resonance frequency of the first mode is decreasing. For example, here, if you have the maximal thickness, which goes from 20 microns to 60 microns, the ratio between the two first modes will decrease to 2.03 to 1.7. So it can be a good indicator and a non-destructive test to evaluate the membrane non-uniformity. We can also see that one of the membrane behaves more like a membrane with uniform thickness, while the other one behaves more like a membrane with a elliptic shape. Let's looking at the frequencies. And using the equation of the frequency presented before, we were able to estimate the space within the membranes, and we evaluated it at 15 to 50 megapascal. Let's now have a quick summary. So we presented useful data for the development of type membranes, such as pressure sensor or microvalves stored in low and harsh conditions. We obtained micro bending results which are consistent with Birch testing results. Vibrometry was used and seems to be a suitable technique to evaluate the non-uniformity of the membrane. Using these techniques, we were able to estimate the effective residual stress in the range of 15 to 50 megapascal, which is quite low for this kind of membrane. So future work will be more focused on the impact of tip gluing to extract both elastic constants and membrane stresses. So I'd like to thank you all for your attention, and if you have any questions, I would like to answer them. Thank you.
Okay, great. So I believe Cornel is here. Hello. Does anybody have any questions? I have one very quick one, and then we'll maybe leave other ones for the breakout rooms. The microprobe setup, how sensitive is the measurement to the position of the microprobe on the membrane? So you've got a 50 micron probe on a several millimeter area. How easy is it to aim to the center? Do you need to get the center?
So yeah, it's quite hard actually to place actually the tip to the pen. At the center of the membrane, so yeah, that's why I use the video actually.
Okay.
So,
Let's
yes.
try again. Sorry.
What you can do is actually to have an array actually of the punch to be sure to have the center, or you can see with you know, the lights coming from that, where is the membrane, if it's a little bit moved, and if you can check actually if you are the center of the membrane, and so you can be really pretty actually accurate on the position of the punch.
Okay, great. But I mean, if you make lots of measurements, lifting it up and putting it down, do you get consistent results, or does it tend to move a lot between each measurement?
No, it is all consistent actually, and yes, but it's better perform this kind of measurement when it's glued. Okay.
Okay, great. All right, thank you. Okay, so if we have another question, we can take one more. Otherwise, we'll move on to the next video presentation, which is, I believe it's a little longer than expected. So what we will do is play the video, and then we will break for the breakout rooms, and then you can ask the questions to the speaker then. Okay. So Pascal, do you have the next presentation? So this is developing MEMS electric current sensors for end use monitoring of power supply. And so this is presented by Liqiang Fan. And sorry, I need to get the biography. They received a BS degree in mechanical engineering from Jilin University, Changchun, China in 2022, or okay. He was with Professor Dong Wang, Microengineering and Microsystems Laboratory of Jilin University, and current research concentrates on cantilever microstrip antenna current sensors and engineering applications. Okay, Please go ahead and play.
Dear professors and scholars, my name is Felix and come from Jilin University. It's my great honor to present developing MEMS electric current sensor for end-use monitoring a power supply Part 10 IEEE 802.11g protocol compliant integratable dual frequency coaxial microstrip antenna. Now, I will introduce it from the following 5 sections: background, wireless cantilever current sensor, antenna design, antenna performance, and conclusions. Now, we come to the background part. Current sensors mainly include Hall current sensor, fluid current sensor, cantilever current sensor, and fiber optic current sensor. Among them, our laboratory team has published a series of articles about cantilever current sensor on DTIP. In order to transmit the cantilever current sensor wirelessly, it is necessary to integrate the cantilever current sensor and the microstrip antenna into a wireless sensor node. In the process of signal transmission, 3 wireless network protocols are involved: IEEE 802.11a, B, and G, IEEE 802.11b. W-line protocol supports the frequency band around 2.4 GHz. IEEE 802.11a supports the frequency band around 5 GHz. In order to make the two compatible, an IEEE 802.11g W-line protocol was developed. The speed can reach 54 Mbps, and the ability to penetrate obstacles is also strong. Therefore, the IEEE 802.11g standard has become the mainstream of the market. Now we come to the next part: wireless cantilever current sensor. Wireless cantilever current sensor is conceptualized and abbreviated as WCCS. Figure 1 is a schematic diagram of WCCS. The cantilever current sensor generates a voltage signal, which is transmitted wirelessly through a microstrip antenna. Figure 2 is the flowchart of integrating of magnetic cantilever with a dual frequency coaxial microstrip antenna, complying with IEEE 802.11g protocol. The dual frequency coaxial microstrip antenna is connected to a series of chips, and finally the voltage signal is sent to the computer terminal. The part is antenna design. In order for the coaxial microstrip antenna to be compliant to the IEEE 802.11g protocol, the microstrip antenna needs to be designed as a dual frequency coaxial microstrip antenna, and its two center resonance frequency are 2.45 GHz and 5.2 GHz, respectively. To obtain a dual frequency operation, the easiest V is let the length of radiation patch of the microstrip antenna corresponds to a resonance frequency. The width corresponds to a resonance frequency. Figure 3 shows the schematic diagram of a dual frequency coaxial microstrip antenna. The yellow upper surface is the patch, and the light blue base part is the substrate. the coaxial feed mode is succeeded for power feeding. Firstly, calculated the size of the dual frequency coaxial microwave antenna through the theoretical formula. The calculated geometry dimensions are shown in Table 1. Import the calculated size into HFS simulation software to get S11. As shown in Figure 4a, you can see from the Figure 4.1 that there are 4 peak points. There are only 1 peak point M1 near 2.45 GHz. It can be roughly judged that the resonance frequency corresponding to M1 is F10, while there are 3 peaks point M2, M3, and M4 near 5.2 GHz. It is impossible to judge which point is the resonance frequency corresponding to F1. Geometry W corresponding to F10 and geometry L corresponding to F1 in order to determine the resonant frequency point corresponding to a special F1. The width W of the patch is used as the design variable to the parametric scan. It can be seen from Figure 4b that increasing the geometry of W, the resonance frequency corresponding to the point M1 in Figure 4a gradually decreases, while the resonance frequency corresponding to the point M2 in Figure 4a does not increase with the geometry of W. The resonance frequency of points M3 and M4 will change with the change of W geometry, so it is finally determined that F10 corresponds to the resonance frequency of point M1 in Figure 4a. F1 corresponds to the resonance frequency and point M2 in Figure 4a, but now the resonance frequency of F10 is 2.39 GHz and the theoretically calculated resonance frequency is 2.45 GHz, which is smaller than the theoretical resonance frequency. Therefore, it is necessary to reduce the geometry of W to make F10 reach 2.45 GHz. The length of width the radiation patch have been optimized before, but in Figure 5c, it can be seen that although F10 and F1 have reached the theoretical value, the return loss at F10 is only minus 3.3236 dB, not minus 10 dB. Below, although the return loss at F1 reaches minus 26.7963 dB, which is lower than minus 10 dB. There is smaller color near F1. This phenomenon are all related to the impedance matching not being adjusted properly. Let's start to adjust the impedance matching at F10. Because the larger L2 is, the larger the impedance value of 2.45 GHz is. So the length of L2 needs to be reduced to achieve the purpose of impedance matching. L2 performs a the skin of 2 to 7 with a skin step of 0.5, which can be obtained from the figure when L2 is equal to 3.2. The characteristic independence of F1 is about 50 ohm. Review the S11 diagram. The resonance frequency at F1 has changed, becoming 5.17 GHz, which is shifted by 5.2 GHz. So we need to continue to optimize the geometry of L so that the resonance frequency of F1 become 5.2 GHz. We optimize the size of L to make F1 reach the theoretical value. Both have reached the ideal value, so the geometry optimization and the independence matching are perfectly finished. Finally, the geometry of the dual frequency coaxial microstrip antenna complying with the IEEE 802.11g protocol is determined as Table 2. Let's start to check the antenna performance as shown in Figure 9 to 13. There no more less the independence and the antenna gain has reached a very ideal value. The last part is the conclusion. In this paper, a dual frequency coaxial microstrip antenna is newly designed. The antenna can work into frequency bands of 2.45 GHz and 5.2 GHz. The return loss at 2.45 GHz is minus 23.0153 dB, and the return loss at 5.2 GHz is minus 21.3685 dB, which is fully meets the standard for the use of microstrip antenna. It can realize the construction of the new physical layer standard IEEE 802.11g protocol and can be integrated with the cantilever current sensor proposed by Dongfang Wang Research Group since 2010. My research is over. Thanks for your attention.
Okay, great. So thanks very much to all of the presenters and those who prepared videos for this session. So I think I'll hand over to Pascal to explain what we're going to do next. We have a coffee break until lunchtime.
Yes, thank you, Stewart. I want to thank you very much for sharing this session. So classically, speakers will join a breakout room to wait for your visit before leaving for dinner or for lunch, depending on which continent you are living on.